Good morning, everybody. If you have not handed over the boarding passes, please do so because it will take some time for us to process the reimbursement. So please hand over the boarding passes, your electronic tickets, as well as the invoice. So we should know the cost of the tickets. So please do that without fail so that we can start the reimbursement process. If you have already provided the bank account number, that's fine. If not, please do not forget to provide your bank account number. And there may be 5 minutes delay because the sound system was tuned for yesterday's concert. So it is being adjusted for the talk. So please hold on. We might start at 9:05. So please hold on until then.
So we are today on the day 2 of our PDC 8 workshop, and today's theme is precursor derived ceramics for thermostructural applications and translational research. And today's session chair is Dr. Stefan Schaffoner. I request him to take over the session.
Good morning, everyone. Welcome to today's first session on precursor-derived ceramics for thermostructural applications and translational research. The first speaker is Dr. Devazia, and he's a scientist and division head of the Ceramic Matrix Products Division with the Indian Space Research Organization. Okay, so the speakers in the morning have 20 minutes, I know, 22 minutes for their talk, and so that we have some time for questions. After 20 minutes, I will give the sign.
Yes. Hello, you can hear me, right? So thank you, Chairman. So the topic of the day is precursor derived ceramics from materials to space applications. And in fact, I come from the Vikram Sarabhai Space Center. It's a part of the Indian Space Research Organization. So I'll be talking a bit on the Indian Space Research Organization. I think the slides are moving on its own. So ISRO as such is having around 34 centers and units around the country. This is a national space agency of the country, and the prime objective of ISRO is to develop space technology and execute the missions of the country. So we are headquartered in Bangalore, and we have centers all throughout, and each of the centers contribute either in one way or the other to the missions. So I come from Vikram Sarabhai Space Center, which is down south in Kerala. Kerala is called God's own country, And Vikram Sarabhai Space Center is a lead center of ISRO. In fact, it is also called the mother center of ISRO because it was started first, where we deal with the design and development of launch vehicle technology. Now, VSSC deals with 14 different branches of research, and chemistry is one of them, and we have an entity called propellant, polymers, chemicals and materials entity, where we deal with the development of propellants, polymers, special materials, advanced ceramics, ceramic matrix composites, and of course energy systems. And this particular team is called CMPD, Ceramic Matrix Products Division. This team was formed in 2005 to have focused research on precursor derived ceramics, ceramic coatings, adhesives, sealants, and ceramic matrix composites. Recently, we have ventured into electrode materials, 3D printing inks, high entropy ceramic materials, and currently we have a total strength of 38, out of which 14 are permanent, and we have 17 non-permanent with students and trainees. So for the work arrangement, we have again subgroups focusing on different aspects of this field. Dr. Srijit is there with me. He will be talking today afternoon on his area of expertise. Now, what we do in ISRO is, we are the only team in ISRO who work on precursor derived ceramics. In fact, we started our work with polysiloxanes. The origin was from polymers. The team was working on polymers, so it was logical to go to polysiloxanes. From polysiloxanes, we parallelly worked on polycarbosilanes. Polycarbosilanes, currently we work on the ultra high temperature ceramic phase modified polycarbosilanes. We also work on boron modified siloxanes, that is polyborosiloxanes. So we have transferred these two technologies to the industry, and we get it back from the industry. We buy it from the industry for our missions. We also have teams working on polysiloxanes and polyborosiloxanes. Now, having worked on the pre-ceramics, it is logical for us to work on the coatings, sealants, and of course ceramic matrix composites. We again started with the polymer impregnation pyrolysis route. We then equipped ourselves with a CVI furnace, and currently we pursue the hybrid route. Well, it depends on basically the component thickness, the throughput time required, and the final properties. In fact, these are two components which we have developed. This is a nose cap of a reusable launch vehicle, and this is a wing leading edge. This is one segment of a wing leading edge. We have 36 such segments to be developed. These are developed by the hybrid technique. You basically combine the PIP process and the CVI process. This is a ceramic fastener. It's an M8 fastener, which was developed completely by a CVI process. This is being inducted into the mission with the RLV. Now, in fact, for the topic of the day, in fact, I thought instead of giving you an overview of all the things what we do, I thought I'll just select one portion, the oxidation protection coating with respect to re-entry applications, and what happens behind the scenes. When you have a successful mission, it comes in the newspaper. Well, failures also do come in the newspaper, but before the success or the failure, what we go through, that is what I would like to share with you, an experience. I have not included all the details, but the salient points. So, well, re-entry missions, everyone knows that it's very complicated, and the slightest problem will escalate to a situation of no return. We have learned too well from the Columbia disaster, and the vehicles get heated up too much, and the heating is basically dependent on the vehicle shape, the entry speed, trajectory, the atmospheric composition, and basically you have two modes of heating, the convective heating and the radiative heating. The message here is the TPS is the single most important component. If it leads to a failure, the mission is lost. So India entered into the re-entry missions with the space capsule re-entry experiment way back in 2007. The mission was launched on 10th January 2007. It spent around 12 days in the orbit. After spending 12 days, it re-entered into the Earth's atmosphere, and it was recovered successfully. With this, India could enter into the elite club of countries having the re-entry technology. Now, the space capsule recovery experiment was a microgravity platform. This was a prelude to the reusable launch vehicles and human in space missions, which we are pursuing now. Now, in the case of space capsule recovery experiment, the TPS, the front TPS was ablative TPS. It's a well-known system, very successful. It has been used in the Apollo missions. It's a rugged system. So, immediately after SRE-1, the SRE-2 was announced. Here the only difference, again it's a microgravity platform, but the TPS changed from ablative to carbon-carbon. The carbon-carbon again was designed as two components. We had a cap and a shell. The cap is having slightly higher density and the nose shell is having slightly lower density. This is designed on purpose so that SRE as such stabilizes in a nose down configuration. Now, well, everyone knows the importance of carbon-carbon. It's an inseparable part of every aerospace mission nowadays. And I will not be speaking on carbon-carbon because this is done by a different team in ISRO. Well, carbon-carbon with all the advantages is having one major disadvantage. It starts oxidizing beyond 500 degrees centigrade. So, if you have to use carbon-carbon for any meaningful application in oxidizing atmosphere beyond 500, we have to protect it from oxidation. Now, this is the requirement given by the project, that is the operating conditions for SRE2. Basically, SRE2 mission is going to face re-entry for just 596 seconds. The heat flux which will be faced will be around 310 watts per centimeter squared, which corresponds to a temperature of 2000 degrees centigrade. The shear values are around 225 Pascal. This is arrived at by the aerothermal team, because we do have a simulation team who takes care of the trajectory and the design. So, this is a design input given to us, and based on this we have to protect the carbon-carbon composites from oxidation. So, the peak heat flux will come at the nose cap at the stagnation point, and this is the nose shell where the heat flux is around 256 watts per centimeter squared. Now, when we have a problem, what we first do is we try to survey the available technology. Well, these are all normal conclusions. Different vehicles have different TPS, and different locations have different TPS, and one size does not fit all. And one easy way of approaching this problem is to go for a historical approach. That is, you use heritage materials which are already used, it's proven, it's safe. Because we are going to this mission for the first time, so we need not take a risk on that. Anyway, whatever technology we use, we have to remember there should be a balance between performance and manufacturability. You should select the lowest density material which provides the most effective protection. So, finally, instead of using a modified matrix on carbon-carbon, we decided we will go for carbon coatings for oxidation protection, which will be a separate layer on top of the carbon-carbon. Now, when we go for the coatings, obviously we have to look at the heritage material. The space shuttles have used silicon carbide, which was basically a silicon carbide conversion coating with a pack cementation technique, and they, to deal with the cracks on the SiC coating, which come due to the CTE mismatch, the coefficient of thermal expansion mismatch, they go for a TEOS, tetraethyl orthosilicate infiltration followed by a sodium silicate glass. Well, the message here is silicon carbide ceramics are the most widely used ones. And when we went for the silicon carbide coatings for ISRO application, we had 4 options in mind. The first was a pack cementation. Well, pack cementation at that point of time we couldn't mature to beyond the laboratory level. It was just in the laboratory level. And chemical vapor deposition, well known technology, but the furnace what we had could not accommodate the SRE nose cap, because SRE nose cap was around a meter, 930 mm in dia. So, it would not go into the furnace. So, we couldn't do it. And siliconization process, again a well known technology, but we were not mature enough beyond a lab. So, finally, we went for a pre-ceramic slurry process, which was very scalable, very easy to do. Now, when we look at a slurry, everyone knows a precursor slurry is very easy to make. Silicon carbide is easier. You simply pyrolyze the slurry to the ample temperature, you get silicon carbide. To get it as a coating is a challenge, a coating which is not cracking. So, we went for the slurry preparation. In this case, we had a pre-ceramic polymer which was polycarboxylane, silicon powder, carbon precursor, silicon carbide. This slurry composition was optimized. We went for 2 types of coating application, a spray coating and a brush coating. We had different levels of heat treatment. Each layer of coating took almost 7 days. The coating thickness was in the range of 450 to 500 microns, let us say around 450 microns, and for 3 layers of coating it almost took 21 days. So, this was the configuration. And how do we ensure that this coating survives? So, what we do is we test these coatings extensively in the ground level. So, we have different types of testing. We have the basic arc jet testing, the radiant heat testing, re-entry plasma ground test facility. And after we complete this test, we again go for some fine tuning. That is, you may have to tinker the coating a bit, and then you have to go for the qualification. This is a rough procedure what we follow with respect to every mission what we do. Now, the first question which was asked to us, do you really need an SiC? This question came from the carbon-carbon team. In fact, they were very confident about the carbon-carbon, especially the high density carbon-carbon. The density was around 1.8, which is quite high for the carbon-carbon, and the re-entry duration was only 596 seconds. They said our composites are not going to erode. So, first we did an arc jet test just on the carbon-carbon. The heat flux, the peak heat flux was used for the test, and we found that we tested both the cap and the shell. In this particular test, the heat flux, a constant heat flux is simulated, which is the peak heat flux. The temperature can be simulated. Atmosphere cannot be simulated. Re-entry atmosphere cannot be simulated because this facility is kept in an atmospheric condition, and the shear can be simulated. So we found that carbon-carbon erodes. Well, beyond 500 degrees centigrade, carbon-carbon is supposed to erode. In fact, we can see the layers coming out, so SiC coating is required. So we went for the SiC coating. We tested ample samples to get confidence from the cap, from the shell. We tested all the samples. Every sample survived. It was a cakewalk. So fine. We graduated to the next level of testing, which is called a radiant heat testing. This is a different facility where we can simulate bigger specimens. So here the heating is simulated by IR lamps. So you do not have shear. This is basically used for the functional testing of gaps and interfaces, for simulating the actual heat flux of the flight. That is, you can have from low heat fluxes to the higher heat fluxes, but this limit is 100 watts per centimeter squared. I cannot go beyond 100 watts per centimeter squared because the IR lamps what we have will not give a heat flux beyond 100 watts. So we used specimens where the heat flux is lower. For specifically the nose shell specimens, we had two different types of thickness, especially from this regime. One is the aft edge of the nose shell. We took a specimen from this regime. In this particular test, we can simulate the actual heat flux and the temperature. Well, the atmosphere cannot be simulated, shear cannot be simulated because it's a radiative heating. So you cannot simulate here shear. Now this is before the test. During the test, the temperatures went up to 1577 degrees centigrade. Then after the test, and NDT, that non-destructive testing before and after showed no flaw or delamination. It was okay. The test was finally it was okay. We repeated the test with a different thickness. Here we tried to understand the thermal response of the material. It's a thick specimen. You give a heat on the front surface. What is the temperature coming behind? We had engineered different thermocouples. What is the different levels of temperature which is coming? That was also studied. Towards the fag end of the test, we found some peel off, but the project team said that peel off happened during the handling of the specimen after the test. So we brushed it off. We said, okay, it was behind, in the back of my mind there was a peel off, but it was okay. But then again we went to the next level. This is like a qualification test for us, the re-entry test, actual re-entry test. This is a plasma arc jet test at low pressure. This is a test which simulates more or less a condition similar to the actual re-entry conditions. So here, we study the oxidation ablation response under re-entry conditions. This test can simulate all the conditions: heat flux, temperature, atmosphere, and shear. So once you qualify this test, this material is cleared for the mission. That was the understanding. Now, we went for the test. We chose the nose cap specimen. The peak heat flux of 310 watts per centimeter squared was chosen. And why this 97 seconds? Because what we do is we always over test the material, so that in the actual flight conditions, the mission is going to face much benign conditions. So when we over test, what we do is we test the peak heat flux over a period of time so that it simulates the total heat load. So this was the re-entry flow conditions. In the first test, SiC eroded. We thought it's an odd man out. We had an erosion, no problem. But again, we repeated the test. We had continuous erosion. All the samples eroded. That was the first taste of failure. We didn't know what to do. Well, we went back to the drawing board. In fact, we were missing something. So first thing, we tried to solve the addition. So the surface preparation was modified. We tried to improve the addition. Then the coating process, we were doing a spray coating. We changed to a brush coating. We slightly increased the coating thickness from 450 to around 600 microns. Then this was an input from the aerothermal team. They found out that the shear on the specimens what we were testing was on the higher side. It was 400 Pascal instead of the required 220 Pascal. So we changed the specimen size so that the shear comes down. And another point was the peak temperature which was simulated is 2000 degrees centigrade. In fact, our thermal team always they add around 20% margin to account for the uncertainties in the thermal model. So in fact, SiC is working on the brink and my material is going to 2000 degrees centigrade. So it's just on the brink. I wanted to bring down the temperature, but that was not approved because it's a ballistic re-entry, and SRE1 time the temperatures measured on the surface was 1930 degrees centigrade. So we had to go with this 2000 degree centigrade temperature. So incorporating the modifications, we tested another specimen, again erosion. Now this is the time when people don't listen to you, because you have too many failures and whatever you say is brushed aside. Okay, you just in fact they were having questions about flying the carbon-carbon at all. They were going back to the ablative system, but then we tried to understand what is the problem. So we went to the literature, we found out how SIC is protecting. This is well documented in literature. So SIC protects by self-passivation. So when SIC is heated beyond 1100, it forms silica. Silica forms an effective crack sealing mechanism, and this is prevalent up to 1420 degrees centigrade. Now beyond 1420, depending on the oxygen partial pressure, what you experience is that silica reacts with the existing silicon carbide, and it can form, silicon suboxide. Now silicon suboxide at that temperatures are volatile. So when you have a shear, the silicon suboxide it starts volatilizing, and this is called active oxidation. Well, up to 1620, you again have silicon forming, and you have again a passive oxidation phenomenon. So you have, in this regime, you have passive and active occurring simultaneously. Beyond 1620, only erosion is happening because silicon suboxide only is formed. This is the reason why the space shuttles work at temperatures below 1600 degrees centigrade. So what we need to understand is passive oxidation is favorable, active oxidation is not favorable. So there is another phenomenon reported by DLR and NASA, where during the testing they found out that when they were testing a material at 1700 degrees centigrade, in fact during the test, as soon as certain conditions with respect to the temperature or pressure is met, the specimen automatically jumps to a higher temperature. So 250 degrees centigrade beyond the operating temperature. So this results in the erosion of SIC. So if you translate both these phenomena to SRE, in SRE when it re-enters, the temperature increases up to 1600 degrees centigrade in 170 seconds. Till 170 it is in the passive regime, we are safe. Then it goes to the active regime where erosion is there, temperature jump is there. Beyond that it comes to the passive regime again. So it travels from passive to active to passive. So basically we will have erosion in the SRE re-entry conditions. So how to protect the mission? So we have to prevent active oxidation and the temperature jump effect. We had two options in mind. We have erosion, why not increase the coating thickness so that you compensate for the erosion? So that was option number one. The option number two was to prevent active to passive to active. At that point of time, we had no idea how to do it. So we went with the new configuration. We increased the coating thickness to 900 microns to compensate for the erosion. Again, we had erosion, but the conclusion was by suitable enhancement of the coating thickness at the stagnation point, the substrate could be protected. That was the logic at that point of time. But then in ISRO, proving things in specimen level will not suffice. I had to prove the concept in the hardware level. So I took it to the hardware. This is the third level of coating. This is a no-shell hardware. Third layer of coating after heat treatment at 900 degrees centigrade. Apparently it looks okay. This is after 1500 degree heat treatment. Again it looks okay in the picture, but if you take a close-up image, you can see cracks. So beyond the critical coating thickness of 600 microns, I cannot increase the coating thickness. So what you see in the specimen and what you translate to the hardware is totally different. So the conclusion is I cannot go beyond 600 microns in this existing configuration. So back to option 2, how to prevent passive to active transition. So this is where one of the teammates came up with a solution of a sealant coating. It's 20 minutes, right? Okay. So came up with the concept of a sealant coating. So you will have a pre-ceramic coating which will be given around 150 to 300 microns over the SIC coating. This will be cured to 175 degrees centigrade. It will seal the cracks if something is formed during the CT mismatch, and it will be a glassy formulation. So the philosophy here is during re-entry, this in situ precursor to ceramic conversion will happen. It's like cooking, and it will consume the heat of re-entry. It will prevent the passive to active transition, avoids erosion of SIC coating. This was a concept at that point of time, and we had to do trials on graphite specimens. The point is, the carbon-carbon team told that, see, you have burned enough specimens, it's very difficult to make new specimens for you. You first prove this concept on graphite, and then you can go for the carbon-carbon. So first this is the morphology of the specimen after the coating. This is a SEM image. This is a slurry coating, so it looks like this. And this is what we did, the coating. This is first bare graphite. The temperatures were crossing 2000 degrees centigrade. 2 specimens we tried. When we put this coating configuration, we got more than what we bargained for. In fact, we had a top of temperature of 700 degrees centigrade. So, it is just well below the passive regime. The mission works in the passive regime. Now, this had to be translated. This is what happens after the test. This is after the test you have a glassy formation as we have expected, and the same thing was translated to carbon-carbon specimens. We could prove the same thing on carbon-carbon, and we were given clearance to do it on the hardware level. It was proven on the hardware level. So, for SRE2 we had developed the hardware, but in 2014 the organization told us to stall all the work on SRE, go ahead with the RLV, reusable launch vehicle missions. So, this is another challenging mission of ISRO. In fact, the chemistry is well known because we have learned too well with SRE. Here we had a nose cap and the wing leading edge, both carbon-carbon. The temperatures were beyond 500. The advantage here is a controlled re-entry. Heat fluxes are low, temperatures are low compared to SRE. So, we have learned it too well. We did the radiant heat testing, we did the arc jet testing, we also did a thermostructural test. Along with the heat, you give point loads. When you give the point loads, you see how the coating is surviving. It survived, and we went for a reusability test without repair. 5 times consecutively we reused the test. We tested again, so that we got ample confidence. This mission was flown successfully on May 23, 2016. It was a successful mission. Now, as we speak today, we have an autonomous landing experiment going ahead in Chitradurga in Karnataka. So, this is going ahead, and this is something which we are working for the future, where we will have a reusable launch vehicle with autonomous landing, where my team is supplying the wing leading edge segments which I showed in the beginning. So, we are using CMCs here. Now, apart from this, we have one more thing. We have a scramjet engine technology demonstrator which we are working. The objective is to bring the launch cost down. We have to take care of the oxidizer we are pumping up along with the propellant. We will take care of the atmospheric oxygen for using for propulsion, and in this case again we had to protect the carbon-carbon components. Heat fluxes were too high. We had to take some of our samples to Russia for the testing because our facilities were incapable of testing. Again, it was a successful mission, again flown in August 2016. Now, for the future, we are working on a scramjet research vehicle which will be an autonomous vehicle, airframe integrated engine and a wing body, where we will have long duration scramjet flights. Here the current materials are totally incompetent. We are moving towards USTCs. So, I think USTCs may be the immediate future. We have just entered into the USTC club, and that is all from my side. Thank you very much.
Thank you. We have time for one short question and one short answer.
Thank you, Dr. Rajit, for this excellent presentation and a very exciting story behind the successful mission. I just want to. Yeah. Okay, I think I'm audible.
Yes, sir. Yes, sir.
Yeah, I just want to understand what type of bonding between this carbon composite and SiC coating.
So it basically
mainly because this will be pyrolyzed. After pre-coating, it will be pyrolyzed around 900 degrees Celsius.
Yes, what we do is we take stoichiometrically slight excess of silicon, so that you will have a reaction bonding happening between the carbon-carbon and the surface of SiC. The first layer of coating will be slightly silicon excess, so that you will have a better anchor.
So that is stable.
Yes, that is stable. Yes, that is stable. Yes.
Okay, thank you. And this test, just want to know about the wear test. Yeah. Maybe discuss later.
Yes, yes, sir. Thank you very much, sir. Thank you, sir. Oh, you're not supposed to. Thank you, sir. Thank you very much.
So, because I realized that we only have 20 minutes for coffee, so that's why we are not allowed to run late. So that's why I was interrupting. So as the next speaker, we have Professor Golo from the Technical University of Berlin, and he's chair of Advanced Ceramic Materials. And in this case, we will He will give a talk about additive manufacturing of PDCs. Thank you. Thank you.
Good. Ladies and gentlemen, good morning. I will talk today about additive manufacturing of precursor-derived ceramics. Like, this title combines two aspects of my scientific research and maybe career I'm dealing with for years. As a precursor-derived ceramics, I'm a chemist and have done quite a lot with colloidal synthesis of metal oxides and colloidal processing to thick films and gas sensors. Additive manufacturing, well, it was a topic I recognized it when I joined a chair in Berlin in October 2014. And like the combination of these two aspects has some advances which I also like to share with you. Well, my talk will be contain the following parts. First, I will briefly describe our activities at the chair in Berlin. Then, go to the broader context of additive manufacturing topic in Berlin. Then describe our activities in areas of materials for additive manufacturing, and go to additive manufacturing of precursor-derived ceramics. And we'll finish my talk with conclusions and outlook. So briefly about our chair. We have like more 1,000 square meter well-equipped lab space, 3 technicians, 5 group leads as postdocs leading several research groups, 1 Eminota junior research group in focusing on catalytic activities, 2 postdocs in the projects, more than 20 PhD students. In 2022, like 4 completed PhD theses, more than 35 reviewed publications, funding about €1 million from several sources. We are part of the excellence cluster about unifying concepts or systems in catalysis, which is led by our university, and also co-initiated 2 large, the big initiatives, activities, dealing with also with additive manufacturing in Berlin. I will talk about that a bit later. Our research focus or approach goes from the synthesis of well-defined materials, well-defined in terms of particle size, morphology, composition, structure, then to application of several fabrication technologies from many different areas like colloidal processing, thin and film deposition, additive manufacturing, to fabricate devices, functional parts for several applications. And also what we quite strong in is the in situ and operando characterization of material synthesis, fabrication, and also device operation. In this images, you see the titles of the books we contributed for, like metal oxides and polymer-derived ceramics, 2 main big areas of materials which we deal with. 1 review paper on in situ and operando characterization of gas sensing activities from the year 2006, right at the beginning when this topic started to grow, and also like 2 examples of applications, metal oxide-based gas sensors and gas separation membranes. I guess it also was like year 2007, 8. Hydrogen separation, we started with Ravi Prasad. Ravi is also here today. Gas separation membranes, so hydrogen separation with polymer-derived ceramics. Also at that time it was like a curiosity-driven research, but nowadays like also in the focus of many activities going around the world. So now additive manufacturing. Well, I joined chair in Berlin in October 2014. at that time, I heard about additive manufacturing, never done it practically. Robocasting, extrusion, colloidal processing, there's several similarities and differences, of course, if you think about additive manufacturing. But then, being in Berlin, I recognized that it's also a topic which really has a significant potential for the future. Why is that? Because first, Berlin is a very specific place. Like, there's no industry there, no large industry there. Like, it was initial birthplace for many large companies, including Siemens, including other large industrial manufacturers. But nowadays, Berlin, what is specific for Berlin? Many startups, digitalization, artificial intelligence, all set aspects, plus some kind of transformation of this classical production technology to this data-driven technology, data-driven production, digitalization in any areas of the life. And also to Berlin organized at that time like a 3D lab, it was called, 3D lab, which combines the expertise of many different chairs and focused on the application of additive manufacturing, especially laser sintering, for like production of mainly metallic parts and polymeric parts. Well, what is now, after this 8 years, they've initiated a large cluster, large initiatives, which is called EMBA, Additive Manufacturing Berlin-Brandenburg. It supported by the Land Berlin, as a state Berlin, with like at this moment 14 million euros in 14 projects that are focused on 4 topics, as a personalized medical technology, construction and lightweight design, additive manufacturing with bio-based materials, and additive manufacturing in or for space applications. In German, expertise of the consort, so in this cluster, which goes from the materials design to digitalization and simulation, as application in different areas, as the materials, manufacture of machines, equipment for additive manufacturing, those technological development and applications. That's one of like a big drivers aspect of additive manufacturing in Berlin. It goes further on, and also will combine several other activities, including the teaching, including also attraction or establishing of new companies in Berlin, and providing space also for new spin-offs and startups. The second driver in our area is the called Werner von Siemens Center for Industry and Science. We started this activity in year 2018. It's like a public-private partnership. Here, the Siemens wants like go back to its birthplace, Berlin, and transform old or established Siemens campus into new Siemens campus to zero, with large investments from Siemens itself and State Berlin, and also providing like a working space and providing opportunity to collaborate for companies and research institutions. We see now partners in this campus, in these co-working spaces. And now also like 3 main application areas, 3 main technological areas in focus of the activities we have there. Again, additive manufacturing, digitalization of the digital twins, and new materials for high temperature applications, especially gas turbines. And also if you think about the transformation to hydrogen-based technology, materials for hydrogen applications. And Siemens has a production technology, production place in Berlin for gas turbines. So, that's like 2 aspects in this context. And next one, spin-offs, startups. We also going to spin off to start up this year with the technology we developed on continuous fiber reinforced printing of polymers, thermoplastics. The print head is our invention. and also provides like a technology which is allows to produce filaments and also reinforcement of plastics with continuous carbon fibers. This was like a third aspect of additive manufacturing activities we do. Another one, if you think about the future, maybe like a very far future, colonization of Moon and Mars, if we have that, the question is how we can do that. And there are several works ongoing around the world in many different places about, they call it ISRO concepts, in situ resource utilization in situ on Moon and Mars. And those several concepts, suggestions to apply to use regoliths from both places, also on Moon and Mars, and to use 3D printing technology to construct either hoses or something else, other parts. We do also go in this direction. Here's an example with quite easy classical slip casting process using the call it Mars, or the Martian regolith simulants, that allows us to produce, fabricate ceramic vases. You see here these parts after firing at different temperatures. It was like a very interesting work, and you see here like from two news agencies, the public, the papers, newspapers. The Berliner scientist plans to establish ceramic production of ceramic fabric on Mars or similar things. Also amazing work. We go further in this direction, applying color additive manufacturing technologies. And another part of that is also outreach with public schools and teaching activities. New master study courses additive manufacturing is in plan, and like we will have 4 new professorships on that topic in coming years. Now, we come to the aspect of the materials for additive manufacturing. This is one of the focus topics at our chair, and what we do, we practically address all that 4 classes of possible materials for additive manufacturing. As the powders, the all classes, metals, polymers, ceramics, resins, the polymeric resins and pre-ceramic resins, the paste, the slurries of different functional materials, the filaments, fill it with metals, fill it with ceramic particles, or also polymeric filaments. There are several classical technologies applied to preform the parts, applied to shape the materials needed for such manufacturing technologies. And you see here several examples of the pilot nozzle for nickel superalloys, for gas turbines. About that we'll talk today in a few minutes, about silicones and silicon oxycarbide ceramics. Then rubber casting of functional pastes, in that case for insulating applications, and also like a startup spin-off and continuous fiber 3D printing. What we have done, we have established a number of technologies allows us to do the pre-processing of raw materials and feedstocks to all IM applications, from powder characterization routes, including the flowability and packing technologies, resin characterization, slurry characterization, filament characterization, etc. And also like post-processing from debeading, depowdering, pyrolysis, sintering, and also chemical and structural analysis of the fabricated parts. And now we are going to IM of precursor-derived ceramics. Well, if you think about especially stereolithography of precursor-derived ceramics or precursor polymers for that, so they need to fulfill several requirements. One of them is sufficient and effective photocarrying ability. This can be done by acrylate functionalization, but in that case we have less commercial available precursors, as a complex chemical modifications is required, and also potential oxygen contamination can happen in that case. We also can blend initial resins or materials with photopolymers But in that case, we can expect low ceramic yield and also potential oxygen contamination. And another route which was explored in the last years is the called thiol-N chemistry. It was previously applied only to polysiloxane, and there are several open questions which require further studies, but also this technology, in our opinion, has a huge potential. It can be transformed and applied also not just of polysiloxanes, but also for other silicon-containing polymers, but also for other metal-containing polymers. So what we have done, like these three important parts, like resin formulation with photoinitiators, scavengers, and other additives, process design, how we can use the specific resins with specific fabrication technology, including also building plates and adhesion between the fabricated parts and adhesion plate, and also the routes to ceramics, as a pyrolysis, which conditions, what should be considered, and how can we avoid cracks during the pyrolysis. We have done it on three classes of polymers, the polysiloxanes, the H62C from Wacker, from Starfire Systems SPR 212, the polysilazane, Durazane 1800 from Merck, and polycarbocylane SMP 10 from Starfire Systems. You can see here the absorption of the absorbents at different wavelengths for photoinitiators we studied to apply it, also DMPA and BEPO. Both of them allows to work in UV range, and with BEPO we can go also to near UV range here and apply UV lamp and the specific wavelengths to start the photopolymerization of the materials. The thiol-N click chemistry is based on a very fast and specific reactions between thiols groups here, and N as a alkane groups, for example, vinyl groups in the polymers and other materials. And it leads to the polymerization, the formation of a continuous network is based on polysiloxanes, modified now with sulfur, the polycarboxylanes, same, and polysiloxanes. The requirement here in that case to have enough vinyl groups in polymers, which we use for that kind of application or that kind of processing technology, and also to control the rate, the speed of the reaction, and also conversion of the initial polymers to this photopolymerized network. Right. Looking at infrared spectra, we can also confirm the consumption of alkane and thiol groups, but also confirmation about the photopolymerization reactions are going on in the polymers. You can see here for all four polymers we studied, decrease in the absorption of the vinyl groups for all of them. The confirmation of the thiol-N click chemistry happens here. And also by doing in situ UV colorimetry studies, we can also observe and control the kinetics of this transformation. For example, here you can see the heat flow for four polymers, all classes we studied. You can recognize it that in both in cases of SPR 212, Durazane 800, and also H62C. The peak time it's about 1 second, meaning we have the maximum heat flow at that time, meaning that also the photopolymerization reaction, the thiol-N click chemistry reaction here quite fast, but it's not the case for SMP10. And it's mainly due to the absorption of photoabsorption of SMP10 by itself. So another aspect was also to develop a manufacturing technology, including also selection of the equipment, as the UV lamps, as the printers, and also printing parameters to fabricate parts, first initially from the polymers and then transform them into ceramics after the pyrolysis. Now in this image you can see like examples of parts fabricated using silane chemistry from polysiloxane SPR212, polysilazane, and polycarbosilane. Different geometries, also different complexities, but in all these three cases, we can achieve layer thickness about 100 microns, exposure time to 4 seconds for printing, fabricating one layer, and also the fabrication is done in fine. And that's what happens after pyrolysis. Here, in that case, we were able to fabricate ceramic parts from 2 polymers, so the polysiloxane and urazane. You can see here optical images for the fabricated parts, plus the tomographic images also for them. The pyrolysis was done in nitrogen atmosphere, temperature about 1100 degrees centigrade, and the fabricated parts basically have no cracks. Some pores inside of them, but basically they are near dense with like a 97% of theoretical density. And also little microscopic images, a tomographic illustrate and show the fine structure without open pores and also with glassy, smooth surface. So, to conclude my talk, so additive manufacturing established now as one of the driving forces for technological developments in Berlin, including many aspects of the commercialization, initiations of startup spin-offs, teaching activities. Additive manufacturing of pre-ceramic precursors, in this broad sense, is a big part of these activities, of this development. The proof of concept is a shift for silicon-containing polymers, and the works with metal-containing polymers and composites ongoing right now. As a further steps, as we see a significant need in polymer development, specifically for the additive manufacturing. Also, manufacturing equipment is not really fully suitable for these specific routes. And also the questions about up and down scaling, as to go to larger dimensions, and also to go to smaller dimensions, to micro-sized parts and nano-sized parts if it's required. There's like 3 directions in which we'll go further on. Okay, thank you for my team, thank you for the funding agencies, and thank you for your attention. Thanks.
Thank you very much. Are there questions?
Yes, also, well, as the first, when we started this activity, also we recognized that there's water on Mars and Moon available, therefore water is also considered in part as a resource available on Mars and Moon. About the atmosphere, we are doing right now this specific simulation or specific, well, in Berlin there's a DLR agency also, is a part focused on specifically on Mars simulation, as a Mars atmosphere simulation. And we are now doing in cooperation like refabrication, reproduction of the Mars atmosphere in our conditions, the glove boxes, to go also with the fabrication technologies there. As pressure, composition, so both aspects we try to consider. Starting with the composition goes into pressure.
Yeah, Professor Gurlov, very interesting talk. My question is, any comments, or rather I would seek your comments on the surface finish that you would get from additively manufactured PDCs, because I'm just wondering, how do you control the surface finish?
So we do not do any specific post-treatment on the parts.
Okay.
Uh,
But you do not have any surface defects or something like that?
Well, not in that terms, like as a, well, defects are especially on the surface which are or was in contact with a build plate. These specific defects are there, but on the parts, on the surfaces which are like fabricated in free space, we do not see any significant or any defects which require further post-fabrication polishing steps of treatments.
Thanks again for the nice talk. And we had a question in the back, but we have to postpone this question for the high tea session. Break.
Thank you, sir. I request Dr. Stefan to present the memento to Dr. Alexander.
I don't know whether it will work. It's a PDF. So very good morning to all of you. Okay, a bit of detour from experimentalist and practical people. So I will be talking about thermodynamic modeling of ceramic systems. So this work I do in collaboration with Professor Ravi Kumar's group, and Neeraja is our joint PhD student. So some results of what is going on in our computational thermodynamics group or the CalFAD lab I will present in today's talk. So roughly this is the outline of my lecture. After the introduction, I will discuss a bit on how first principles computations can be integrated with CalFAD modeling, and then I give a glimpse of what is meant by Gibbs energy modeling and what is the approach generally people take, and also I will touch upon the model parameter optimization, where we use a lot of inputs from experiments. And then finally, I will discuss some results from the database that we are developing, that is a thermodynamic database for metal nitrates. Okay, what is the aim of this kind of a work? So CalFAD is a very general technique. It can be applied to any material. Of course, the assumption is that we look at materials under equilibrium conditions. So we develop Gibbs energy functions for describing the equilibrium nature of many classes of materials. Of course, in this particular talk, I will be concentrating more on the nitrogen containing metal nitrogen systems, which is the basis for understanding the metal nitrates. Now, what is the utility of this kind of approach? So obviously, the name CalFAD comes from the fact that the technique was originally developed for describing the phase equilibrium or computing the phase diagrams, calculation of phase diagrams. Of course, that is one of the main functions, and it can be of course used for many other purposes wherever you need Gibbs energy functions. For example, describing chemical equilibria or computing thermochemical properties, which is of use for many purposes, and or simulating the phase transformation kinetics, because one of the main input that is required to describe kinetics is the thermodynamic driving force. So this comes from Gibbs energy functions. Then finally, of course, these days people can also integrate this with microstructure simulation tools such as the phase field technique, which is very popular in some of the research groups. So to do all this, what we require is high quality input data. So the reliability of the input data or the quality of the input data actually determines the quality of the functions that you generate. So of course, input data is any kind of data that you can relate to Gibbs energy functions. So you can think about all kinds of phase equilibria data, thermochemical property measurements. In some systems, we also require describing the effect of magnetism on the Gibbs energies. Of course, in this context, it is not so important, but for metallic materials, any magnetic materials, it is an important input. And basis of modeling for solids are on crystal structure. So we have to know the crystal structure before we can model the Gibbs energy functions of solids. Now, data comes mainly from experiments. So what happens is that many of these kind of materials, which are very difficult to handle in an experimental measurement, like measuring thermochemical properties or phase equilibrium of ceramic systems, are quite tedious because many of them require extreme temperatures. Equilibration is difficult. So often we have a lot of shortage of data. So what can we do when we don't have sufficient information? Can we really model? Because modeling requires input data. So there are allied computations. The results from such computations can also be used as an input into this kind of a modeling technique. If such things are also not possible, there are many ways of empirically estimating the properties. So for example, there are many estimation techniques for thermochemical properties. Many of them are empirical. So any input, whether it is experimental or generated using theoretical techniques or empirical estimation, all these can be used as an input. So once we have created an input file, then you have a process called optimization, which I will tell you in a minute. So the output of any such exercise is a set of Gibbs energy functions. So these functions are obviously functions of temperature, pressure, and composition. So information that we generate is with respect to all these conditions. Temperature dependent information. Pressure is typically taken as the atmospheric pressure, because pressure dependent data is very difficult to generate, although it is important in some systems, except for gases. Then of course composition. So as a function of composition also, you can measure many of these properties or generate these properties. So these will all go as an input, and the result will be therefore Gibbs energy functions. In principle, one can describe as a function of temperature, pressure, and composition. So as I mentioned, major challenge in any of these exercises is lack of reliable input data. So when you have that, we have these estimation techniques which we could use as an alternate. Okay, just for the want of time, I will skip this because we have only, I think, 10 minutes, I suppose. So this is basically a flowchart of the entire procedure. So it will take some time to go through it, so I skip this. Now, as I mentioned, nowadays the tendency is that to fill the experimental knowledge with other computational techniques. So one major activity is to combine the results of so-called first principle calculations with computational thermodynamics. So how do we do that? So nowadays we have a lot of very powerful first principle calculation codes. For example, in our lab we use a code called VASP, Vienna ab initio simulation package. So using this package, one can generate a lot of thermochemical data that is useful for the input for the modeling. For example, we can calculate the enthalpies of formation of various compounds, which is a critical input for the Gibbs energy modeling. So combined with some temperature dependent calculations, which is called the phonon calculations, we can generate heat capacity. So all the first principle calculations are generally, the results are for 0K. So how to introduce the temperature dependence? We have to use these phonon calculations, which repeatedly call the VASP code, and we can generate temperature dependent information. So one very useful output that we get from this kind of temperature dependent calculation or the phonon calculation is the heat capacity, which is basis for developing Gibbs energy functions for any material. So heat capacity data along with the enthalpy of formation data will give you reasonably good Gibbs energy functions at the end. Obviously, we will also combine with whatever experimental information that is available. So at the end, we do an optimization using all these input and generate the Gibbs energy functions. So the programs that we use in our group, WASP I have already said, for phonon calculations we use a code called PhonoP, and for the thermodynamic modeling we use mostly thermocalc. So these are all some of the software that we use for doing this kind of work. Now just a glimpse of what is this Gibbs energy modeling. So one of the challenges to model a multi-component multi-phase system is to have a Gibbs energy model which is more like a universal model which can be applied to any type of phase, because if you look at a material system, there may be some phases which are stoichiometric, some may be having a composition dependence because it can exist over a range of composition, some have very completely disordered like solid solutions, some may have long range order. So all these things we have to address during the modeling. So to do such a modeling, we need to have a universal approach. The sublattice formalism is one such universal approach that can be used to model different types of phases, so that you don't have to look for different types of models for different phases. So this is one formalism which allows you to construct Gibbs energy functions for many different types of phases. So this is the general expression which is the basis of modeling of the Gibbs energy functions of the phases. So it is quite simple if you split the expression into three parts. So there is the first term, which is the first summation term. This is called the contributions from the compound energies. So this term is also the term which sometimes referred to as the reference term. Then you have a second term which is the configurational entropy term. It comes from the configurational contribution or the entropy contribution to the Gibbs energy. This last term is actually the deviation from ideal behavior, because most of these phases are non-ideal. So there will be some deviation from the ideal behavior. So that is accounted here. Most of the time we spend in developing Gibbs energy function is in these two parts, because these parts would contain model parameters. So those model parameters are what we have to estimate through this optimization, which requires all these kind of input. So basically somebody who is doing thermodynamic modeling will be spending a lot of time to figure out the coefficients that describe these two parts of the Gibbs energy function. So this is what is stored in a database. So when you use a program like thermocalc or similar computational tools, they have a large collection of such coefficients. So this is read, and then you can do all the other calculations like phase equilibrium calculations or calculating thermochemical properties, or you can even transfer it to some other programs to do types of computations like the microstructure simulation and things like that. So that is how the Gibbs energy models work. Let us skip this. So this is just the explanation of how this can be applied to a certain phase. I have taken example of this mixed nitrate, hafnium tantalum nitrate. So this is a phase with large non-stoichiometry. So which means that in the nitrogen sublattice there is a lot of vacancies. So we have the metallic sublattice, and then these are the interstitial positions or the octahedral positions metallic in this mononitride crystal structure. So these numbers here are of course the stoichiometric numbers, and these numbers come from the fact that for every substitutional position there is an octahedral void which is partially occupied by the nitrogen, the remaining vacancy. So VA here is the vacant octahedral positions. So you can see that this if you use this kind of a model to describe this kind of a nitride phase, you will end up having this kind of n members. So n members are those compounds which are actually stoichiometric compounds which describes the first term in the Gibbs energy functions. These energies of these compounds are actually that what is called the reference term. So that is therefore the basis of developing the functions, the energies of these compounds. Obviously, this is binary nitrate, hafnium nitrate. This is pure hafnium. This is tantalum nitrate, and that is pure tantalum. So Ta colon V means the entire octahedral positions are now occupied by vacancies, which means it is pure tantalum. So obviously, this tantalum is in the same crystal structure as the nitrate, which is the sodium chloride structure. So obviously, you know that these are metastable, because hafnium is at room temperature it is HCP, tantalum is BCC. But these energies are energies of tantalum and hafnium in the sodium chloride type of structure. So this kind of energies also we have to estimate. So there are techniques to do it. That is, these are all metastable modifications of these elements, which are obviously experimentally not accessible. So we have to use some other techniques to generate these functions. And these two classes of the N members, or I cannot say these are N members, these are called the constituent arrays. So these constituent arrays are the arrays that describe the excess part. So modeling the energies of this will lead to the last part of the Gibbs energy function, which is the excess part. So that is how the modeling works. Okay, let us skip all this. The process of optimizing, that is how to obtain the coefficients which describe these functions. So what is that you need? You need obviously models. So this model is based on sublattice approach. So you create a file which describes the model, and then you create another file which has all the input data that is required to regress this model. Together, you combine these two through a process called compilation, and then you create a work file. Then this work file is used for the optimization, and it is a repeated, it is an iterative process. You keep on refining the fit by changing the weights or changing the order in which you optimize the parameters. There are some strategies, and this is where we spend a lot of time, how to optimize these Gibbs energy functions using these input file and chosen models. So many times you have to go back and forth, and at the end you generate these coefficients which are stored in input files which we call thermodynamic database files. So you can combine several of such database files for binary systems to describe the thermodynamics of a multi-component system. The power of this technique is that the modeling is usually done only for binaries and ternaries, assuming that all the unary functions are known. So once you combine all this, you can actually start describing a multi-component system. So it doesn't matter how many components are there, how many phases are there. So that way this technique is very powerful to deal with multi-component, multi-phase systems. But the modeling work is always concentrating on binaries and ternaries. Then we do what is called an extrapolation. That extrapolation is quite powerful. Usually we see that very minor adjustments are only required to correct something in the higher order systems. So that is the power of the techniques. So these databases are therefore meant to do calculations not only in binary and ternary systems, but also in multi-component systems. That way you can even take care of even the impurities which are present in your system. So many times when you synthesize materials, you will have some unwanted oxygen or some other elements. All these can be taken into account, provided you have Gibbs energy functions to describe those kind of effects. So that is the power of the calculations. It can actually address multi-component, multi-phase systems, and the basis is Gibbs energy functions for these single component, binaries and ternary, and then combining it through a geometrical technique, and then you can do calculations in the multi-component systems. Now to remaining part of my talk is just results of some of the things that we have done in our group in last 4 or 5 years. So most of this is done with, as I mentioned, with collaboration with Professor Ravikumar's group. So experiments are usually conducted with his help, and then we use those input to model some of these systems. So this is an example of the modeling of the, so we are actually after these metal nitrogen systems, and these are the metals that we have currently considered. So many of these binaries and ternaries we have already established the Gibbs energy functions. Obviously, as the time goes by, the list gets expanded. So we build it over a period of time. So last 5-6 years, I think about 1 or 2 PhDs have already come out of this collaborative effect, and it grows as a function of obviously time as more and more modeling work is addressed. So this is an example of zirconium nitrogen system, and then this is titanium zirconium nitrogen. So this is a mixed nitride. How the enthalpy of mixing changes. So we can already see that the mixing is resisted. So titanium nitride, zirconium nitride, when you mix, the enthalpy is increasing, which means that you should have a miscibility gap if you plot the corresponding phase diagram. So which is obviously seen here. So titanium nitride with zirconium nitride has a miscibility gap. So at low temperature, it is a two-phase system. Only at very high temperatures, it will behave like a single-phase solid solution. So obviously, there are no experimental evidence for this. So somebody has to perform an experiment and see whether indeed true. In some thin films and all, they have seen this kind of phase separation. But in bulk materials, I don't think there is any data which shows that we have these miscibility gaps. So this is what the theory predicts. And similarly, for zirconium silicon nitrogen, we have some results. So these are some of the calculation results. For example, this is a comparison of the isothermal section calculated for this ternary system. So there are some experimental data, and which is being compared with the calculated results. As a matter of fact, you can calculate these kind of sections at any temperature, because most of these functions are valid between 300 to up to about 4000 Kelvin. So at any temperature, you can generate this kind of information. So it is up to us at what temperature we want to do calculations. And in addition to that, you can also calculate several other types of phase equilibria, like the one I showed you, the quasi-binary sections of two nitrates, things like this. All this can be calculated using the same database. Okay, so recently we started looking at a tantalum nitrogen system. This is part of Neeraj's PhD work. So this is the experimental version of the phase diagram. So what is interesting to note that some of the compounds which are predicted to be stable is not part of that experimental phase diagram. For example, this is what is called a convex hull construction. So basically the information comes from DFT calculations. So DFT calculation shows that you have two other compounds which could be stable. So you have this Ta5N6 and Ta3N5. So obviously these compounds are already reported in many literature, and they have some practical application. For example, I think Ta3N5 is used in electrocatalysis. So there are people who are able to synthesize them. So obviously these have to be included in the phase diagram modeling. So what we did is, of course, very little information is available with respect to its phase behavior, especially thermochemical properties. So some computations were done to generate that. So using those results, we could model the tantalum nitrogen system with these two compounds now included in the phase diagram. Obviously, this is what is called the condensed version of the phase diagram. You can also include the gas phase. So instead of removing gas phase, we can keep the gas phase and then generate another version of the diagram which includes the gas phase. So all these things are possible once you have the Gibbs energy functions. So now that time is up, I am done. Thank you. Yeah.
Thank you. Other questions?
Okay, there are no questions?
No, there is one question, but they have problems with the microphone.
Fine.
Maybe we take another question first. So, in the meantime, I have a question. So, okay, he has a question, and then we come back to you.
Yeah, Professor Harikumar, thank you very much. I think wonderful, actually, maybe the target to derive the phase diagram from Gibbs free energy change. Just one small thing, I'm not sure whether I'm right or not. Do you think that we need to consider enthalpy changes and entropy while we are computing the Gibbs free energy?
Yeah, this is part of the function. No? So any Gibbs energy function would have two parts, the enthalpy part and the entropy part. So every term in that expression which I gave you, which is written as G, you can break that into an enthalpy part and an entropy part.
But
So
I have not seen into the flow chart that part.
it gets modeled together because we see enthalpy information comes from calorimetry.
Right.
And then we have heat capacity data, which is an indirect information about the entropy. In addition to that, we have configurational entropy, which is basically compositional effect.
Yeah.
The second term in the Gibbs energy function is actually configurational entropy contribution. The thermal contribution comes from heat capacity.
Yesterday we had a good presentation. I think maybe that also can be okay.
Yeah, so those things are taken care. The enthalpy and the.
We take another question from the back.
Sir, very nice presentation, thank you. Sir, I have many questions, but I will ask 2 questions. Sir, you are calculating the CP using the phonopy. And so for phonopy, sir, you are getting the phonon density of states.
Yeah.
So the phonon density of states, are you calculating individual element or you are calculating as a whole?
It's as a whole. So we create a supercell, and
Okay.
then any phonon calculation requires a larger cell, no? So
Yes.
the entire supercell is used in the simulation. So we make perturbations and then calculate the total energy. Then E versus V curve,
Yes.
we estimate the properties.
And sir, the stabilizing, you showed the binary compounds stabilization. So when we will go for the ternary compound, ternary, quaternary compounds, how the stabilization means, what are the aspects you look into to stabilize the system?
See, when you talk about ternary compound, I would assume that it is a compound that exists only in the ternary. So there are 2 things. One, a binary compound extending into the ternary by dissolution of something.
Okay.
So that is one
Yes.
way of, so for example, you may stabilize some nitrate by adding, let's say, carbon.
Okay, okay.
So these kind of things are taken care in the modeling. So obviously to model such things we need some information about how the phase equilibria changes as a function of adding a third term. So that is one possibility.
Yes.
Another possibility is to have a totally new compound. For example, I talked about, I showed one plot, one
Yes.
silicon, zirconium, nitrogen.
Yes.
That is a true ternary compound that exists only in the ternary.
Okay, okay.
So that is, of course, if there is knowledge about that, we look for how to generate its thermochemical information, which is a required input. So for that compound, we didn't have any experimental data, but we could generate the required data through the combination of this first principle with phonon calculations. So that goes as an input.
Sir, in
No,
this
no,
case-
sorry.
Okay.
I have to interrupt at this
We,
time.
we can talk.
Sir, I
Yeah,
will-
you have to talk later, please, in the during the tea session. Sorry.
Yeah, so I will take my
Thank you,
bag.
sir.
Yeah.
First,
thank you very
Stefan
much.
sir to present the memento.
Next is online.
So the next lecture is by Dr. Gurpreet Singh. Unfortunately, he couldn't come here, and so the lecture is a recorded one. I request everyone to just look at the screen and listen.
Yeah, he was supposed to come, but he couldn't because of the semester being on. So therefore, he sent the recorded lecture so that we don't lose time and so on. So we hear the recorded lecture. So I think he will also be listening to this. I mean, he's there, but I'm not sure whether he can take questions.
everyone. This is Professor Singh, and for today's presentation, I'll be offering you a brief overview on the recent progress that our group has made in the silicon-based precursor-derived ceramic materials in fibers, CMCs, but more importantly, electrodes for beyond lithium-ion battery technology. Okay. So this is we are involved in many different things involving PDCs in my lab, and these are some examples of it. We're looking at PDCs as battery electrodes, ceramic fibers for CMCs, coatings for thermal absorber coatings for power meters, and we also have interest in 3D printing, and we indeed collaborate with Professor Paulo Colombo some time ago. And I would encourage you to take a moment and look at this website, which has the list of available projects in these areas. In addition to my regular research and teaching activities, I'm also the director of the National Science Foundation Partnerships in International Research and Education project on polymer-derived ceramics. This is a very large international effort involving PDC materials, and we have experts from within the US as well as in Europe and Asia. For this project, we have the purpose behind this project was to jumpstart the PDC research in US universities. As you may be aware, Europe and Japan are leaders in pre-ceramic polymer chemistry, but more importantly, PDC fiber drying processes. And this kind of research is non-existent in US universities, although there is some effort ongoing in national labs and industry. So the idea behind this project was to reach out to our friends across the Atlantic and foster relationships and create a workforce here in the US that can then go and serve the industries, especially in the area of ceramic matrix composites. So here, this is an education and a research project. So we have three research teams, and those are listed here on the screen. We are interested in development of low-cost pre-ceramic polymers that are suitable for fiber drying processes. We are interested in understanding the polymer to ceramic transformations. And then there's also interest in characterization of mechanical properties and especially high temperature properties of ceramic fibers, and then coupling those with the molecular structure of the pre-ceramic polymer. And so we have 5 countries involved, 10 universities involved outside of the US, and some of those partners are listed here, as you can see. And then within the US, we have 5 universities, and those include Kansas State University, Arizona State University, University of Colorado, University of Texas, Lehigh, and MIT. We also have the General Electric company as one of our industry partners. Okay. So this slide here shows some of the research themes that my group has pursued through the NSF Fire project over the years, and also some of the outcomes. So as I mentioned earlier, the pre-ceramic polymers that are amenable for fiber drawing are typically not available here in the US. So those are either need to be sourced from outside of the US or they need to be made in the lab. So our initial focus involving PDC fibers was focused on just working with whatever we could find within the US or locally. So we started with these cyclic silazanes that are available in the US, one of which is shown here. And we realized very quickly that this liquid phase free ceramic polymer is either a oligomer or has a short polymer chains, or it's actually a mix of cyclic and branched and linear oligomers. And this kind of precursor does not possess the rheology in order for us to allow fiber drawing. So one need to be able to tune the rheology and to make it amenable for fiber drawing processes. So our initial focus was on applying thermally induced cross-linking to play with the rheology. And we realized very quickly that these thermally induced cross-linking processes are not controllable. So for example, if you have a liquid pre-ceramic polymer, as you can see in the left side graph here, and then you try to apply some heat to it, the change in rheology is rather sudden. So, and there is insufficient time to draw fibers from these precursors. So that was something that was limiting us from drawing fibers from these materials. So we worked in collaboration with our partners in France and also Italy, and they suggested that maybe we can introduce some sort of a spinning agent. So that's what is shown here in the middle of the slide. We were able to introduce a linear organic polymer, and that allowed us to tune the rheology and of this hybrid organic inorganic polymer. We showed that we could draw fibers from it, and these were then pyrolyzed to obtain carbon-rich SiCN, which is electron microscope of graph, electron microscope image of which is shown in the slide. Then later on, our efforts focused on siloxanes. Especially, we were interested in scaling up, the hand drawing processes as we were demonstrated, with regard to SiCN is not scalable, obviously. So we were interested in looking at other precursors that would allow us to some way of scaling up this process. So we worked with ring siloxanes and also linear siloxanes, and all of these are actually available here in the US. And we found that these kind of siloxanes allow electrospinning with minimal amount of organic precursor. So here we were able to demonstrate fabrication of large area non-woven fiber mats, which were stable up to very high temperatures. So this work was published in RSC journal. And then more recently, we are focusing on introduction of nano fillers, especially those that are analogous to graphene, with the goal to tune the rheology of the pre-ceramic polymer and then draw fibers from it, with the goal that such fibers will possess high strength because of the presence of nanofiller phase. And this is something that is based on our review of literature. There, in fact, some evidence that introduction of exfoliated graphite or graphene in carbon fiber lead to 2 to 5-fold increase in strength. And so in our case, graphene obviously would not work. So we are looking at high strength nanofillers that are analogous to graphene, but can survive high temperature as well. So we're looking at MOS2, for example, and boron nitride. And more about this in following slides. And then with regard to CMCs, we are in the final year of the PIRE project. And so in our conversations with industry and also funding agencies, we realized that moving forward, the focus is going to be on CMC materials and not just the fibers. So in here, I show one of the works that recently came out from our group, where we demonstrated fabrication of mini composites from SiCN, SiPCN, and SiHFCN matrices with carbon fiber as the reinforcement. And indeed, the quaternary ceramics show improved oxidation resistance compared to neat SiCN. And so I would suggest that you take a look at this paper. In addition to that, we also have interest in CMC, micro-city of CMC. This is something that is being pursued in collaboration with the University of Colorado. Here we are interested in looking at creating 3D maps of the CMC and figuring out the reasons for example, the presence of void and how to eliminate voids, and how the presence of void affect mechanical properties of a CMC material. Okay. Now, in addition to CMCs, there's also interest in use of PDC fibers and composites for electrochemical energy storage applications. And this is mainly driven by the fact that PDC materials allow wide range of compositions. So you can have SiCN, SiCN, SiOC, and metal modified SiCN, SiOC. And then in addition to that, the unique microstructure of PDC materials. For example, these are, for example, in case of SiOC, it could be single phase amorphous or 3-phase amorphous. You can have microvoids present in your material. You can have carbon-rich SiOC. So the microstructure is also tunable depending on the precursors and also the pyrolysis environment. And this has implications in the storage of charge in these materials. For example, lithium-ion batteries in case of A, in case of B, if you have a hard you have a excess carbon-rich SiCN or SiOC, for example, then those are probably more suitable for sodium-ion batteries. And then high surface area SiOC suitable for supercapacitor applications, and then also as a host for sulfur in lithium sulfur battery cathodes. Okay. So following slides, I'm just going to be focusing on our efforts related to batteries. So just a little bit of background. This is a schematic of a lithium-ion battery cell. So this is now common knowledge. There's hardly any scientist who does not know how a lithium-ion battery works. You generally have an anode material, which is graphite, and cathode material, which is some lithium compound. Lithium cobalt oxide is the common one, and you have some electrolyte that is separating the two. And what is not common knowledge is that these so-called graphite anode and lithium cobalt oxide cathode, these are not in their pure form. They are not used directly. In fact, these so-called electrodes are composites. So generally, you are introducing some sort of a conducting agent or binder material, and then these so-called anode graphite is slurry coated on copper foil. In case of cathode, it is slurry coated on aluminum foil. And this has consequences. So as a result, what happens is, due to the presence of these metal foils and binder, conducting agent, porosity, about 50% of the cell mass is inactive. So it's not contributing to the capacity of the cell. And that's a big number. So if you want to, for example, if you're a battery scientist and you want to develop a cell with high energy density, then one can think of somehow eliminating these dead weights. And indeed, our group is focusing on that. So we are interested in moving away from this traditional design, which is shown on the left-hand side, which has a metal foil and conducting agent and binder, and then active material is the only one that is contributing to the capacity. Our idea is to have one integral material, for example, PDCs, which could act as a conducting PDC, for example, a carbon-rich PDC material, which could be in the form of a self-standing film or fiber or composite, and it may act as current collector, active material, and also as a charge as a conducting agent. And these kind of structures are possible in case of PDCs because they are suitable for making low-dimensional structures. So that's and these can also be load-bearing, for example. And indeed, our group has made important contributions in this area for lithium-ion batteries. I recommend that you take a look at some of these journal articles where we demonstrated fabrication of these self-standing electrodes from PDCs for lithium-ion batteries. As far as our interactions with battery community and funding agencies concerned, we are being asked a different kind of questions. We are being asked if PDC materials have applications in, for example, low-cost sodium-ion batteries or potassium-ion batteries or lithium sulfur batteries, for example, for large-scale storage or bigger vehicles. So we are trying to answer that question, and this generally comes because of the fact that the elements that go into preparation of, for example, anode and cathode material of a lithium-ion cell, those are scarce and they are non-uniformly distributed. And then in addition, there are concerns about environmental impact. So if you compare lithium with sodium, sodium is abundant element and it's more uniformly distributed in Earth crust. Also, there has been and the cost will be lower. And there have been studies that have shown that if you simply replace lithium-ion battery with sodium-ion battery, for example, then one can expect 30% cost reduction. And this is taking everything into account. Even the folks that are most pessimistic about sodium-ion batteries, even they agree that 4 to 5% reduction in cost is possible by switching sodium ion battery with lithium ion battery. Okay. So if you look at it, there are actually already this slide here shows the cathode and the anode material for lithium ion battery and sodium ion battery. So there are already, because sodium is stacked below lithium in the periodic table. So there are already cathode materials out there like that are analogous to cathode material for lithium-ion battery. For example, for every lithium cobalt oxide, there is sodium cobalt oxide available. But if you look at the bottom where you have the graphite, there is, we do not have, those are the anode. So we do not have the anode material for sodium-ion battery at this moment. In fact, that is a one big hindrance to commercialization of sodium-ion battery. Okay? And for potassium-ion batteries, there are even more issues. We can talk about those later. But the key is that if we can find a low-cost material that can cycle sodium at room temperature without degradation, that would be wonderful. Right? So we started in this slide. What you see is the data for graphite. So this is a cell that may be made in our lab using commercially available graphite. And what you see here are the voltage profiles. So on the y-axis is the potential, and the x-axis is the capacity, which is generally measured in milliamp hour per gram. So it says black one here is the first cycle insertion, and it's going down, and then extraction, sodium coming out. And what you see here is that for sodium, a graphite system, we see a capacity that is 25 milliamp hour per gram, the red one here. And you see that is roughly 25 milliamp hour per gram. Now this value is much lower compared to lithium graphite system. For example, in case of lithium graphite system, we get 370 milliamp hour per gram. So it's clear from this slide that graphite is not going to work as an anode for sodium-ion battery. And this is, like I said, is not new. This is something that we just wanted to confirm. And then so we said, okay, let's try PDCs. So so far we have only tried one system. So we looked at this silicon oxycarbide material that is being prepared from TTC as precursor. And here are the voltage profiles for that. And what we notice here is the red one here where it ends at, that's the charge capacity, that's the useful capacity. And we see that charge capacity is roughly 3 times that of graphite, about 3 to 4 times sometimes. So there is considerable improvement moving away from graphite to PDC, but still this value 75 milliamp hour gram or 90 milliamp hour per gram is still considerably lower compared to lithium graphite system. And so that's something to keep in mind. Okay, and then another experiment we did with potassium ion cell. So here's the data for silicon oxycarbide, and we are inserting potassium into it, and we are extracting potassium. And what we see here is that for this also for PDC material, we have charge capacity, which is the green and the red one, the second cycle and third cycle. The charge capacity is 15 milliamp hour per gram, which is again significantly lower compared to lithium graphite system. So which leads us to the conclusion that PDCs perhaps are not suitable for sodium and potassium ion and chemistries, at least PDCs in their pristine form, and at least the SiOC system, and they're not likely to be competitive compared to lithium graphite system in terms of which simply because the capacity is just too low. Then we thought, okay, are there other options out there that can, are there other ways for us to use PDCs in some other way, in case of these sodium and potassium cells? So we look at these materials in the literature. These are transition metal dichalcogenides. These are materials that are analogous to graphene. And so these are compounds. So there are 40 different types that exist, where M represents the transition metal atom, and X represents the chalcogen, which could be sulfur, selenium, or tellurium. And just like carbon, these can form fullerenes, for example. They can form nanotubes, or they can form nanosheets. And these materials were studied were actually discovered by Recep Tayyip in Israel, and also Bharat Ratna C.N.R. Rao worked on these materials and made important contributions to these materials. And so what we find is that if you make an electrode from this material, for example, any of the TMDs, in this case MOS2, we see that we are able to insert sodium in these materials reversibly. And the capacity that you're getting here, the red one, you're seeing it is about 400 milliamp hour per gram. Now, That's quite significant. That is about 25 times what you would get for graphite. And the reason for this high capacity in these materials is the unique reaction. So the reaction that you see in a TMD sodium system is quite different from your sodium graphite, for example. So here the sodium ions chemically reacts with the TMD in case of MOS2, and it can do that reversibly at room temperature, and it's a 2 to 4 electron process compared to lithium graphite or sodium graphite system, which is a single electron process. So here you are able to store more charge for given mass of the electrode material. However, this material this is the data from our experiments conducted in my lab, and we see that initially for the first cycle we see 400 milliamp hour per gram roughly, and then in subsequent cycles of charge and discharge, we see that there is capacity fading observed in these materials for sodium ion cells, for example, in this case. And this capacity then fades very quickly, and within few cycles, we are starting to see 50 milliamp hour per gram. And this kind of a capacity fading has been reported by other groups as well. And it has been suggested that this could be due to large volume changes happening when the sodium is inserted in the material because of the conversion reaction, and as it leaves the system during the discharge process, charge and discharge, for example. And also the dissolution of sulfur chalcogen into the electrolyte. And so we thought, by the way, this is something we also see in case of potassium ion cells. So the data for potassium ion cell is reported here. We see that TMD show high capacity toward potassium as well. And so it works for both of them, but the only problem is that of capacity fading. So in order to suppress capacity fading, we came up with the idea, how about we functionalize this TMD material with PDC, because the PDCs are prepared from nanoscale liquid phase precursors. In theory, one should be able to exfoliate this TMD material in a liquid phase pre-ceramic polymer and then pyrolyze, with the hope that this PDC would form monolayer, for example, silicon oxycarbide or silicon carbonitride, depending on the precursor, and protect the TMD from this degradation reaction with the electrolyte. Okay, so that's the idea. So what we do is we use this pre-ceramic polymer, TTCS, which is a siloxane, and we take TMD in case of WS2 crystal, for example, and then we create a solution of this WS2 in TTCS, and then we do the electrospinning with the goal that this exfoliated TMD material will get embedded in the PDC fiber matrix. Indeed, so these are the results for that. On the left-hand side is the Aspen fiber mat, then the fiber mat after cross-linking, and then the fiber mat upon pyrolysis at 800 degrees C. Then some microscopy data, we see that depending on the loading of the TMD, the fibers could be uniform, or if the loading is too high, the fibers tend to become non-uniform and the fiber mat becomes more brittle. And then we utilize Raman spectroscopy to confirm that the TMD structure has been preserved upon pyrolysis, and then that the SiOC leads to formation of the free carbon phase network, which is important to maintain the electrical conductivity. And then we make these cells, in half cell in an argon glove box. And then here's the data. This is the key here. So you have already seen the first 4 graphs on the left-hand side. Pay attention to the one on the right-hand side. That's the data for these composite fibers. And what we see here is the charge capacity, as you can see, is close to 500 milliamp hour per gram, which is higher than, which is much higher than SiOC, neat SiOC, but comparable to the TMD material. And you can also see in the bottom graph, you have these sharp peaks, which suggest that the crystalline structure of the TMD was retained even after first and second and third cycles. And same thing for this is the data for potassium, insertion of potassium into these composite fiber mats, and then here again we see that the capacity is significantly higher than neat PDC material. And then in the bottom one, you can see those sharp peaks that represent oxidation and reduction reactions And it seems like the crystalline structure of the TMD was preserved. And then, but more importantly, this is the cycling data. And you can see we are comparing here on the left-hand side, sodium ion cell. On the right-hand side, we have the potassium ion cell. Black one represents the neat TMD. The red one represents the composite of TMD in PDC fiber. And it's clear from this data that the degradation or the capacity degradation was suppressed due to the presence of TMDs in this PDC matrix. So this is a significant result in our opinion. And so with this, I would like to summarize the data. I think it's clear that international collaborations are critical for advancement of PDC science and technology. As you can see that we have benefited through our collaboration with partners across the Atlantic and in Asia. Likewise, our friends have been able to send their students to my lab and other labs within the US. And so it has been mutually beneficial. And on the technical side, we have shown that PDC materials still have use in sodium and potassium ion cells, perhaps not as an active material, but as a protectant material for other high capacity sodium or potassium anode materials. And this, in fact, is the first report involving use of freestanding fiber mats, composite fiber mats of PDCs for sodium and potassium cells. In future, we would like to conduct some in situ analysis to see what is happening to the microstructure as the sodium is inserted and extracted out of the system. With this, I would like to acknowledge our partners from IIT Madras and University of Bayreuth. We still have an ongoing collaboration with them, at least with IIT Madras. With University of Bayreuth, our connection is somewhat limited. I only realized later on that I had one student in my lab, Eloisa Ramlo, who had spent time in Professor Guntermo's lab, who happened to be involved in organization of the workshop. So with this, I would like to thank you for your attention. Questions?
Thank you. Thank you, sir. So with this, we have concluded our first session of the day. And I request Dr. Ravi Kumar to present memento to Dr. Stephan.
If we have to start exactly at 11 o'clock, we need to bring the coffee here. I suggest that because if we have to maintain time, we will have to compromise a little bit, get the coffee and come here so that we can start on time. Thank you.
works.
So welcome back, everyone. Moving to the next session of the day, we have our session chair, Dr. Caroline Sitzman. I request every speaker to be stick to the time allotted to them, as we are already running 10 minutes behind our schedule. So over to you, Caroline.
Thank you. Welcome to the next session. So the next talk will be of Paul van Losbrecht, I'm sorry, and he's talking about hybrid perovskites. So.
Is it working now? Yes. I'll have a bit unusual talk in a way. I'm a physicist and my interest is primarily in fundamental properties, not necessarily applied, and you'll notice that in my talk. As already mentioned, my name is Paul van Loosdrecht, University of Cologne, and what I'm going to talk about is today is about hybrid perovskites, which became very much focus of interest of many people because of their application in solar cell technologies, right? So it's a sort of a very promising method still at the moment, I would say, with efficiency up to 20% or so. So that sounds very good. And then there's stability issues, the fact that there's lead in there, and all kind of other things which one has to solve before that this actually becomes a real killer application, so to say. But these hybrid materials, they are actually known for a very long time, and they have been studied for their physical properties also for a very long time. And yes, solar cell application, that's what's made it in the last decade or so extremely popular. But towards the, the 70s, 80s of last century, there was a lot of interest in magnetism, quantum magnetism. I'll tell you a little bit about that today, optoelectronic applications, spintronic applications, multiferroic behavior, optical switching. Nearly every physical functional phenomena there is, you will find them back in the hybrids. And hybrid is here defined as perovskite-like structures which are partially organic, partially inorganic. And on the left side, you see one of the structures. This is a two-dimensional hybrid, which means that let's say the transition metal, they form corner-sharing networks, which in this particular case is two-dimensional. In the solar cell applications, there you have three-dimensional structures. As I said, it's a class of materials which goes way back when. So I think one of the first reports, maybe the first, I didn't really fully investigate, is from 1884. So this is how long these materials are actually known. And I put here on this previous sheet, this new there, because some 10 or so years, 15 years ago, there was like big papers, oh, there's a new material here. That's how new they are. Yeah? So this is, sometimes with new one has to be a bit careful. There's actually quite a nice review on these materials from 2016 by Mitzi, who's done a lot of work in these materials, which is very, I can highly recommend, so to say. Yes, solar cell applications, but this is a little bit older, 1999, where it's already shown that in this case this was a tin-based material. You actually can very easily build thin film transistors out of it, and that's something which people nowadays are trying to do in an efficient way with these types of materials again, but also this dates already back some bit more than 2 decades. These initial sheets I just used to try to show you that there's actually a whole world of properties there and materials actually, with different dimensionalities. So this is, as you see it here again, this is called a 2D material. There's also 1D, 0D, 3D, and all of them have interesting properties. And what I'll do today, because it's a relatively short talk and we were in time pressure, I understood a minute ago, I'll try to tell you about 3 different things in these materials. One is related to this magnetism, this quantum magnetism, where you can show that you can optically actually control the magnetic properties of these materials to some extent. And then I'll show 2 short experiments related to, let's say, the current interest in these types of materials. One is to how optically measure effective masses of charge carriers, which is of course one important property for photovoltaic applications, and another important property is the home mobility, and I'll tell you a little bit about that too. So let's start with the magnetism, and as we saw a few sheets back, many of these materials, they have lower dimension. So what I'll do here today is talk about 2-dimensional variant. So the essential ingredient there is copper chlorine as a sort of the transition metal octaeder. And that means it's a 2-dimensional, in this case it's a 2-dimensional structure, and if you think about magnetism, there's a problem with 2 dimensions. And the problem arises actually from the fact that any material will have quantum fluctuations, and if you have nothing dictating a direction in the system, then the quantum fluctuations will be so large that this material cannot order. So you have the spins, they order, right? But the quantum fluctuations are simply so large they flip all the time, so there's no order. That's if there's no directionality at all. That's called a Heisenberg magnet. So here, for those who are interested, is the Hamiltonian. There's just spin-spin interactions when A and B, so when all components have the equal interaction strength, then it's called Heisenberg. When not, then there's a directionality to the system. And you can take an extreme case where you only have this term, which means they all want to be aligned along each other's z direction. In that case, you actually do get ordering, and that's shown here, for instance, in the heat capacity as a function of temperature, where you see that, for instance, in the Heisenberg case, in 1 dimension or 2 dimension, there's no real ordering peak there. In 3 dimension, there is. And for the Ising case, you see that in so in 2 and 3 dimensions it's ordered, but still in 1 dimension you still have a problem. So that's what makes these materials interesting from a physics point of view. It's very unusual magnetism. Now the one I want to talk to you about today is these copper chloride structures with ethylammonium or methylammonium in there, and it's that here there's phenylethylammonium in between, so be a bit creative in getting the right thing in between. What's the interest here? 2-dimensional corner sharing octaedra. So we have planes. In the planes we have spins. The spins interact. Interaction strength is something like 20 Kelvin, and they're really almost 2-dimensional because these planes, they're simply far apart, so the magnetic interactions are very weak. And that means it's almost two-dimensional, so it's sort of the ratio between the interplane and the in-plane interaction is somehow in the order of 10 minus 5. And then inside the plane, there's still an anisotropy, so there's some directionality for the spins, for the magnetism, and that means they have they're not fully Heisenberg typically. Yeah? And this in-plane anisotropy is sort of in the order of, again, 10⁻⁵. And if you put everything together, you can actually calculate what is the transition temperature, and this is in the order of 10 Kelvin. And if you measure the transition temperature, you find out it is in the order of 10 Kelvin. Yeah, so in that sense, these are actually fairly well understood materials. Well, one thing which is funny, if you take methylammonium as the sort of connecting molecule between the layers, you get a ferromagnet. And if you take ethylammonium, which is from a physicist's point of view the same, let's put it this way, I'm sorry, then you get an antiferromagnet. So this coupling between the layers, so in the layers it's always ferromagnetic, but the coupling between the layers depends a lot, crucially, on what exactly is the connecting molecules, basically. And so that's depicted here. So if in methylammonium variant, you have ferromagnetically coupled ferromagnetic layers. In the ethylammonium variant, you have antiferromagnetically coupled ferromagnetic layers again. And the reason for that is that in this particular case, the reason it magnetically orders, so it's a 2D system, and it still orders, and the reason it orders actually is that there is an in-plane anisotropy. So there's a single ion anisotropy, if you like, whereas in the antiferromagnetic case, the interlayer interaction is so large, relatively, that it becomes three-dimensional, and then orders for that reason. So they have different ordering, but also different reasons to order. Now you can, so one, we control this. Can we study the dynamics in this, control it? And the answer in the end is yes. And the type of experiments we do is we do pump-probe spectroscopy, which means somehow we pump the sample, trying to change the magnetism, and then probe whatever happened to it. Now the probe is somehow in the DD transition, so this is the optical spectrum of these compounds. Simply looking at the Faraday effect, essentially. But the pump is a bit special here because we pump actually in the charge transfer transitions. And if you do that, you change the occupation of your orbitals, obviously. But with that, you also change the anisotropy in the system, the single ion anisotropy. And the excited state simply has a different single ion anisotropy than the ground state then. And that's really what one can use. So if you pump that transition, you influences the anisotropy. And the way we look at that is actually we look at something which is called coherent spin precession. So by pumping that, what we do actually, apart of making this, you make a sudden change in the magnetic properties, if you like. And if you do that, you launch an excitation in the magnetic system, which is called a magnon, if you like. Spin precession, so your spin sort of start to rotate. And it turns out that if you do that in this methylammonium variant, then by the time you get in the vicinity of the phase transition, you get an enormous response. So what you see here is the time response of the magnetization in the end. This is the Faraday signal. And you see that the magnetization oscillates, which means that all the spins sort of nicely together oscillate. And in the vicinity of the phase transition, you see an enormous enhancement of that. Whereas in the other case, you also see these oscillations, but they're weak. And in fact, there's nothing particularly going on near the phase transition. And the phase transition is around 10 Kelvin or so. You can work that out, and then you can just plot, let's say, the amplitude, so the size of how strongly can I influence the magnetism here, actually, as a function of temperature. And then you see that, indeed, in this methylammonium compound, there's like a divergence at the phase transition, whereas the ethylammonium compound couldn't care less, so to say. And the reason is, and you can also actually really demonstrate and calculate things, is that in the methylammonium, the reason to ordering is this anisotropy, and we were actually increasing the anisotropy by optically pumping here. And that's why simply the magnetism essentially gets stronger. Yeah? So TC goes up a bit. And that's sort of encoded in here, and that describes really the data we see here as well. So that is one example of simply physics in these kind of hybrid materials. As you notice, no application perspective as such, yeah, unless somebody is very creative, maybe here in the audience. So let me go to a different topic then, to the let's say the perovskites of high current interest. And one thing is in these lead-based perovskite materials, there's, at least from an application point of view, there's questions about the properties. What exactly is the mobilities in material, not influenced by the measurement method, for instance. If you do a transport measurement, you can also measure mobility, but all kind of charging effects and domains or whatever, they kind of could mess things up. Effective mass is another question. And what I'm going to show here is using transient absorption spectroscopy, that you can actually measure these properties using optical techniques. And this is based off, if you do a transient absorption spectroscopy, you can you change, I'll think of a semiconductor typically. There's a number of things you can change. Suppose that you pump the system and your band gap changes. Yeah, you get a specific change in your optical properties, which you can measure, and from the shape of that, you can actually tell how much is shifted. Then there's bleaching, you start to saturate if you strongly pump, saturate transitions, which means that the absorption strength becomes a bit less, so you get a negative signal. You could have induced absorption. You can have broadening due to coupling to phonons, or you can have also narrowing, all kind of things. Yeah? So I'm not trying to give a lecture on transient absorption spectroscopy here. The point is that there's a lot of things you can learn from this transient absorption spectroscopy by really in detail analyzing the data. And the one thing I want to talk about now is actually a combination, well, mostly about this last thing here. This is the Moss-Bernstein Moss shift. This has to do with if you optically pump a material, then of course you have made holes here, you made electrons there, which means the next one you excite should come from here and should go up there. So there's a larger transition energy than in the ground state. Yeah? So there's a shift of your optical spectrum actually. Yeah? That's one thing. And the other thing is that if you have a lot of highly excited electrons, you change the Coulomb interactions in your system, and that leads to a change of your crystal potential actually. And that leads to a change of the band gap itself. So there's two things which change the energy, if you like, of your transition. This one actually decays very fast, and this has a little bit longer decay time. So if you look at late times, you essentially see that guy. Now, what does that have to do with the effective mass? A bit depicted here. So what you have here is the transient absorption signal. This is actually for different pump energy, and what you see is that, yes, there's a shift, and that's sort of recognized by this nice S shape. Yeah? But you also see there's a kind of a broadening of the whole signal. If you pump higher, it just gets broader, and that is because you get more and more population. Yeah? And now, getting more population, this of course follows, let's say, the structure of your band gap, your filling density of states. And how the density of states exactly looks like depends on exactly what your dispersion is. So by looking at this, and looking at it in time and modeling it, you can actually work out that this band, this energy shift you should measure, the broadening actually, is given by essentially the excited state density to the power 2/3. Yeah? Times 1 over the mass, the electron hole mass. And that's the effective mass of your electron hole system. Now this density you can just measure by the number of photons absorbed. Yeah? And that means that the only parameter left we have is the effective mass, and that means that if I now analyze my data, for instance, I see that this width is sort of linear in the density to the power 2/3 as expected, and then from the slope we can just determine that the effective mass in this material is 0.14, so they're relatively light, which makes them actually very good semiconductors. And this is one of the reasons behind why, it's a small reason, but still, why these materials work so well as solar cell materials. Another question is about the mobility of charge carriers. And in this particular, you would like to know it from the electrons and the hole. In this particular case, this is a particular example. I will just tell you about the hole mobility. And again, what we use is a transient absorption type of technique. This time on maybe a sort of at least a application, more application relevant layer. So here we have our hybrid perovskite. And what we have here is actually a Hall acceptor layer. What really happens now is that if I, so this is the energy structure of it, if I excite essentially my hybrid perovskite, these holes, they will be extracted from the material and go into the PSS. And you can study the dynamics of this, and that has to do with diffusion in the, that has to do with the mobility. So if you look at the dynamics of this process, you learn something about the mobility. What is plotted here actually is the absorption coefficient structure of energy. You see there's a band gap. We have two different films with two different thicknesses of our active layer. And they have similar band gaps, slight deviations also in the excitons. And then, in addition, what is plotted in green here is the transient absorption spectrum in delta OD, negative. It's bleaching after pumping the thickest film. I'll come back to that in a minute. And what we typically do, we pump band gap. So we simply introduce carriers in the system because that's what we want if you want to measure the charge carrier mobility. Well, so you can do that. And what you look at is, so if you make these transitions, you make this electron hole pair in the perovskite material. Yeah, what you at the same time then do, you bleach the transition. So your transition probability goes down. You get a negative change in your optical density, and that you can trace as a function of time. And that's plotted here. So here is the change in your absorption as a function of time normalized for two different cases. One is a thick film, 170 nanometers. One is a thin film, 40 nanometers. And there's one obvious difference. The thin film is much faster. And that means that this has nothing to do, and even, well, from the type scale, it could nothing to do with the radiative decay or any other. It must have to do with the thickness of the film. And that's obvious because this is how the experiment was designed. Yeah. This is much thicker, so charge carriers which are sort of created over here, they have to somehow diffuse to this P.PSS, at least the holes, to stop this bleaching, so to say. So once you lose it, then actually you can make the transition again, or at least half of it. Yeah. And that's the reason why these timescales are so vastly different, even though the films are only a factor of 2-3 different in thickness. Now again, you can model that, so it's really nothing else than a diffusion equation in one dimension. So it goes, in the end, it goes somehow, this time scales goes with the square root of the thickness, the square of the thickness or so. And that's why they're so vastly different. But you can model that, and the drawn lines here, sorry, no, these are actually just fits. these are actually simulations. And you see that the numbers are essentially the same coming out of the simulation and the fit. And this is a full-scale modeling, meaning you take care of that the initial charge distribution in your sample after a short pulse of light is not a flat homogeneous distribution. And then you just solve, essentially your diffusion equation as a function of time. So what's plotted here is the density of charge carriers as a function of time going down. And then you can translate that in these curves. And fine, so you can understand it, but the important question was, do we learn something? Yes, we learned something. What we get is the diffusion constant, which is about 0.03 or 0.25 centimeters squared per second. And from that, using Einstein's equation, you can actually calculate what is now the hole mobility, and it's 1.0 something centimeters squared per volt second. And this indeed is one of the other reasons. So this is very high compared to, for instance, organic materials. Still very low compared to gallium arsenide. but it's still one of these other very good reasons why these materials are actually so in their optoelectronic properties. Now I heard the bell already. The bell is for the last 5 minutes, I assume. I didn't, but that's good. So because this is all I wanted to, I didn't want to do too much today. So what I showed you a little bit is that in these hybrid materials, you can actually do something which is maybe not necessarily relevant for this community, but from my point of view, quite interesting. You can control the magnetism there to some extent. And you can use these optical techniques to get very clean measurements, if you like, for instance, the effective mass or the whole mobility. And there's actually other properties one can consider or probe as well. And with that, I come to the end. I showed you a variety of short stories, so there's many people involved here, partly from the University of Groningen, and then there's quite a number of people from the University of Cologne, which apart from my own group, it's a group of Sanjay Mathur, who's, as you know, also here, and the group of Klaus Meerholz. And then there are some more collaborations, in particular on these 4 cation materials together with the group of Sanjay Mathur. And with that, I would like to end and thank you all for your attention. To speak.
Really nice talk. I think there is no sound here.
It works.
Hello?
It works.
It's fine? Okay. Okay. So my question is about, I mean, when you have this hybrid perovskite, there is a phase transformation also happens with temperature. And depending on the kind of centrosymmetric nature of your crystal structure, there could be the repercussion on the electronic band structure and also the effective mass. So these are with which particular crystal structure, I mean, which phase of the crystal structure that you are talking about?
This is all in the, so the last two, they are both in the high temperature phase structure. If you go down in temperature, indeed, in particular for the lead iodides, they get a phase transition which is not so nice for the properties, indeed. So this was all, the last two at least, exactly, were all room temperature.
Okay, great. Thanks. Really nice talk. Thanks.
There's the next question.
Thank you, Paul. I have actually a query about the second part where you have shown these two film thicknesses. Is there a correlation between the lifetime of holes, so diffusion length, lifetime, and an optimal film thickness? Because in both the cases, 40 and 170, you have the same amount of charge carriers being generated. So the charge carrier concentration was apparently the same.
Not necessarily. I mean, they because they have different thickness, and the penetration depth is not that deep, at least for the light we use.
Yeah.
And that means that that's why you have this inhomogeneous distribution of charge carrier, which means that in the thick film, the density is slightly lower than in the thin film. But that's a technical detail which in the end doesn't matter. To your first question, that is relevant, right? I mean, if your charge carrier lifetime for whatever, radiative, non-radiative decay is much more shorter than, let's say, the diffusion time you need to get to the interface, then you have to take that into account. Yeah? In this case, it's so long-lived it doesn't matter. But it does matter in the end. And okay. There are other materials where you can't even do this experiment because you lose your carriers before they actually reach the interface.
Right, okay, thanks. And just one more thing, is the defect concentration playing? Because in thin film, the defect density will be different than what you have in a thicker film where the grain boundaries are more pronounced.
Well, surprisingly, in this case not, as you saw that the diffusion constant are kind of the same, and of course, having defects in your system, it does many things, but first of all, it will reduce the diffusion constant, typically. And they're very, very similar.
Please, one short question.
Hello, yeah. So I have a question regarding the first part about the optical control of the magnetic anisotropy. What's the precision with which we can control the anisotropy? What's the precision?
Precision? Oh, that's a good question.
So perhaps you can talk about it at lunchtime?
We can talk about lunchtime. The short answer is you can't measure how much you really change it. So the precision is probably in the order of 10%. You can calculate, but there's assumptions in there, so it's not too precise. Okay, 10% maybe.
Thank you.
Good. Thank you.
Thank you.
I would now
Again.
request Dr. Carolyn to please hand over the memento to Dr. Paul.
And we get a picture together. Wow. Thank you.
So our next speaker is Sudip Chakraborty, and he will talk about computational roadmap of hybrid perovskite materials. So, welcome.
No, I think I have. Okay, do not turn on. Okay. Just put it here. Let me just do it. I'm audible?
Yeah,
Okay.
you are.
Okay. Should be fine, right? Yeah. Great. Okay. So thanks, Chair. Good morning. So first of all, I would like to thank Ravi for inviting us, and it's the second time here in last probably 4 months, and also Gunther for the nice arrangement and the IGSTC. And I think it's really nice to be here last couple of days. I would also like to thank Sanjay, who actually connected Ravi with me a couple of years back in a true sense of Indo-German collaboration. Yeah, and I would also like to thank Paul for the nice platform that you provided just before my talk on the hybrid perovskite. I was a bit shaky about if there will be anyone who will be actually kind of appreciate this particular community of research in hybrid perovskite. So I'm from Harish Chandra Research Institute. Some of you may not know. So this is an institute under Department of Atomic Energy in Government of India. It's purely theoretical institute, so we don't have any experimental groups there. But I mean, I was lucky to have a lot of experimental colleagues around the globe where we are doing the collaboration. And so today what I'm going to talk on the computational roadmap of, is it audible or it's fine? Okay, there's some, okay, anyway. So I'll talk about the computational roadmap on the hybrid perovskite. So it was really nicely complemented with the previous talk. And before that, what I'm going to start with the nutshell of our research. So what we do, we kind of develop atomistic modeling codes and their application for the different energy. It's mostly in the solar cell, battery, and also in catalysis. I'll be talk mostly on the perovskite for the solar cell today, but I will also touch upon a few things what we do in the other area as well. So one of the kind of development that I'm kind of involved with Professor David Wells in Cambridge with the transition pathway prediction, which is basically kind of be in every field of materials. I mean, if you want to know ion migration, that is important in the battery, that is important in the perovskite, and also it's important how fast the water is splitted. So it's kind of quite kind of a useful technique to know. What we have done here, we have kind of tried to do a new technique, which is kind of replacing the old NEB technique, because in NEB technique you have the initial and the final point, but here you only have the initial point, and then you see the whole energy landscape. The second development, what's happened? Okay, it's on basically the nonlinear Poisson-Boltzmann solver. So this is basically when you have a solid-liquid interface. So most of the DFT calculation or any first principle electronic structure calculation, you have the gas phase of those kind of material simulation. But in the real material simulation, you also have a liquid, that is the electrolyte. And you need to take care that thing, that electrolyte dielectric constant also in your calculation. So there is a PCM, there is this implicit solvent model There is also explicit solvent model where people are trying to put it on the water, kind of putting explicitly on the top of your surface. But what we are trying to see is more kind of fundamentally from the nonlinear Poisson-Boltzmann solver perspective, trying to put it in the DFT Hamiltonian, try to see that. I'm not going to tell all these things today. One of the application that we kind of do, that is said about, I think some kind of a lag here, with this ion migration. The second one is actually trying to understand the hybrid perovskites, their efficiency. But efficiency is not only the main thing, you also need to have a stable perovskite, because you cannot do anything if you have really super efficient solar cell material, but if you put it on your rooftop, it will be melted or it will be distorted after some solar irradiation. So you really need to answer the question about the stability. You really need to know how the stability could be enhanced. And the third thing is the solid liquid interface, where we are trying to see the catalytic reaction mechanism actually. So if it's mostly for the heterogeneous catalysis. So a brief about the energy materials. I think we all know why we are doing energy materials, so I'm not going to spend any time on that. I would just like to emphasize the last one. So the interdisciplinary research is also in the energy related field, where you can see the battery and also solar cell can also go hand by hand. And I think if you'll kind of answer the fundamental questions of such kind of materials, I mean, why exactly the electronic structure is changing, why the optical properties are changing, you can actually have the answer for the other areas of energy as well. So what kind of, why we are here, I mean, trying to kind of answer the question why materials modeling is important. It's kind of a haystack model, so I can kind of explain with this. So basically, this haystack is kind of the plethoras of material that we have or that we can synthesize. And there you have to kind of ask to find a needle here, which is a particular material for a particular application. It's too difficult, you cannot really do that. And I mean, what this, okay. So this haystack is too big due to the periodic table, and you cannot really do all the material synthesizing in your laboratory to kind of see which could be the proper application for a proper material, for say. So I mean, it's really required a big army for that, and our funding is quite limited. So what we do, we try to kind of simulate those property in computer, mostly in supercomputer, basically in the high performance computing facility, and then we try to kind of relate those property to see if we can actually get something out of that. So here this guy is trying to use the magnetic property, which I think Paul was talking in the last talk. So in the similar way, we also try to get the electronic property, the optical properties, or some other ion migration properties, and try to see, okay, this will be the optimum material for optimum application that one can do. So I kind of convince, hopefully, or kind of for my self-satisfaction, that materials modeling is actually in real demand, and it will be in more in the next few years also. So a bit of kind of evolution of the atomistic modeling, those who are not quite aware of it. So we kind of, I mean, it's all started, I mean, so this classical and the quantum mechanics is always there. You cannot really solve the Schrodinger equation for many electron system. And then you have, I mean, all these things, there's evolution, I'm not going to details of that. If you have any kind of question, you can always approach me. So what we are trying to be in this particular regime, which is the density functional theory, where you have the density of the electron in order to take care of the materials property there. And that you want to do. And that is basically our workhorse. So we have our own in-house codes, which is this particular transition pathway, and then this solid liquid interface. And then we also have these codes, I mean, these different high performance computing codes, where one can actually see different properties. So this VAS, PhonoP, GPO, in the VAS you have, I mean, you can actually calculate the, basically many things like, I mean, electronic properties, you can also calculate the reaction coordinates. You also have the solvent effect in VAS, so that you can also know how the heterogeneous catalytic system can work. In the PhonoP, let's say if you want to kind of synthesize some material, but beforehand you want to predict those material, And if you want to see if that particular material is stable enough, dynamically stable enough, then you can actually see the phonon dispersion. And from there, one can actually see, okay, this particular material could be kind of good enough for synthesis. So this was our kind of workhorses. And so what I'm going to talk today, so these are few of the works. So I'll be mostly talking on the applications. So these are few of the works that we kind of did. So it's kind of a threefold in a way. And so these are the publications that we did after I came back to India from Sweden and before in Germany. So I was in IIT Indore first, and then I moved to HRI. And I think our main focus of studies there is actually first is the catalytic reaction mechanism, and then you have the battery, where we are doing a lot on that, on ion migration, and third, we are trying to see how the hybrid perovskite works. So I think with Sanjay, we are working on that a lot recently. Actually, not recently, like for last couple of years. Yeah. So so what I'm gonna say today is not all the things, but I'll just kind of limit myself to the last one, that is the hybrid perovskite material, and trying to say one particular or couple of particular example, how exactly one can actually see them. So if you want to read any other papers, you can always go to our website, and if you have any question, you can always approach me. I'll be available to discuss. So, and this is another in-house code I just want to kind of show, because this was kind of done, I think, more than 8 years now, but we are still developing it, where we are trying to see the transition, the ion migration for a confined system, where you have a quantum confined system. So this work was with Professor David Wells, where we developed the code, and then Claire was there in Cambridge. She has some experimental results, and then we tried to kind of complement those results, which was kind of properly verified or explained, which was not in one of the 90s paper in Gert Seder's group in Electrochemica Acta, where he was actually showing that the lithium and amine are kind of going together. But that's not the case. That is, they're actually going one by one. So I'm not also going to talk on that. But if you would like to read anything on that, you can always read and tell me. So as I said, I'll talk on the hybrid perovskite material, and these are the things. This is a kind of a landscape of hybrid perovskite. So it's all started. I think Paul has already made my job a bit easier, kind of explaining what exactly the hybrid perovskite and how exactly things are there. And so one can see. One can play around with different elements in the hybrid perovskite. One can play around with the organic cations. One can play around with the halogen. One can play around with the PB or SN in order to get the non-toxicity in a material. But one can also play around with the electronic structure and the optical properties, and also the ion migration. So I think in this first work with Professor Mark Asta in Berkeley and Professor Subodh Maselkar, we tried to kind of see different possible high throughput computation, where we are trying to see the high throughput computation of all possible perovskite, which are like lead free, so that we can actually see if we can actually find some good materials to hand over to our experimental friend, that was Subodh, and if they can synthesize that. So that was one of the things that we did. In the second work, it's more, I'll kind of come at the later part of the talk. That was more kind of the perovskite material for neuromorphic computing, where we're trying to kind of explore the neuromorphic computing with the ion migration pathway and try to correlate where, how exactly we can actually enhance the property of the neuromorphic computing in those perovskite materials. So this was mainly done with Maxim Kovalenko in ETH Zurich. And the third one, where we are trying to see how the stability, as I was mentioning, that how the stability of the hybrid perovskite material, or for halide perovskite material also could be tuned. Because what happened, we have seen many papers where people kind of doped something with some other things, but kind of not quite, I don't get the clear picture of how exactly it's been done. It may not be quite stable. So you need to calculate the formation energy or the dynamical stability for the phonon dispersion, unless it's quite hard to tell. So these are another things that we do. So I'll just talk briefly. What happened? Okay. so the high throughput computational screening that we did, where we started with all possible, we have a good computational resource in HRI. So it's around 4,000 core for the moment. It will be upgraded next. So what we are doing is actually trying to kind of explore all possible configurations in the crystal structure from the ICSD, and then we go to the next level of structural selection on the formation energy based structural selection. Then we also do the phonon dispersion based dynamical stability. Then the next refinement is on the fundamental band gap and the optical response and the spectra from there. And then you have the effective mass. I think Paul was nicely explaining how the effective mass could be quite related with that. And also there is a question about the anisotropy in the effective mass. So one can actually see from the band structure perspective how, if there is any anisotropy in the band structure. And we actually seen from the spin texture perspective if you can actually see the anisotropy there. So you can actually measure that as well. The step 5 where we are trying to see more accurate calculation, because if you will have a lead in the system, or if it's not lead also some heavy element in the system, the relativistic spin-orbit coupling really matters a lot. And I mean, so there are many papers where people don't consider the SOC or spin-orbit coupling to get the things faster, but that's not probably the correct way to do, because then you are kind of missing out a lot of physics behind you. Because if you don't really consider the spin-orbit coupling in a heavy element, one can actually kind of not seeing the band splitting, the Rashba splitting there. And that is one of the important thing for the charge carrier recombination, which you could be kind of connected with your different possibility of LED or be it in solar cell. So this was the second thing. So previously it was, I mean, what we actually did is, sorry. Okay. So once we kind of selected the material, so we started with, let's say, 100 of different possibility, and then we kind of get down only to 10 such material, and we just gave it to our experimental colleague, and we only published only one paper out of the 100 materials. So yeah, but it was nice, enjoyable work. So the second thing what we are doing, as I was just telling in the last slide, that the spin-orbit coupling, the effect of spin-orbit coupling, it's tremendously important if you have any heavy elements in your system, and second of all, if you have a non-centrosymmetric structure. So your non-centrosymmetric structure comes from, I mean, in your perovskite material, you have the cubic orthonormal tetragonal structure, or if you have a 2D perovskite material, you're kind of breaking the inversion symmetry for that matter. So in those cases, you kind of breaking the non-inversion symmetry, so you have a non-centrosymmetric structure. So what happened is actually your valence band and the conduction band, which was all super good in the normal cases, they actually get splitted. And as they splitted, this excited electron which is there in the conduction band, they cannot really come directly here, but they go to some here, I mean some other metastable state there. So what you are doing, in principle kind of tuning the charge carrier, I mean the electron hole recombination, because you are kind of delaying the electron hole recombination. So as a matter of fact, if it's not there, and if you really want to kind of make the electron hole recombination delay, one can actually put a pressure or a strain. I'll come to that in the later part of the talk. So it's totally up to you. So it's all kind of win-win game, I would say. So if there is kind of a electron hole recombination, if it's not that great, you can always try to see those material for the LED application. If there is more delayed in the electron hole recombination, you can always pursue it for the solar cell. So never give up if something is not happening for a particular application. You can always find another application with some creativity. And if it's not there also, you can also try to put some external strain or something like that to change those. So it's not always, okay, I want to make the solar cell, I have to make the solar cell. It's not. If I fail, I can do some other things in the same way. So if your fundamental electronic structure is kind of clear, and then I think you can do anything with that. Okay, so we kind of wrote a perspective on that, on the Rashba phenomena, which was here. And then we also have done some calculation to see. So this was actually the one that I'm going to show a bit after, I think. after this few couple of slides. So what you can say is that, I mean, if you kind of play around with the electron hole recombination, you can actually do a lot many application in a principle. So one can see the solar cell application with the efficiency. One can calculate the light emitting diode application. We are recently doing in our computational lab, try to see the Rashba assisted catalytic property, because at the end what you are actually tuning is the electrons, and that kind of makes your system good catalytic or not. So if you have the control over that, you can actually do many things together. So the last thing we're actually trying to see right now, so hopefully we'll have some good work on that in near future. So oops. Okay, so I'll come to it's good that it skipped anyway. So this was one of the work where it started with CS2AGBI BR6 system, and this is a cubic. So it's all super good with kind of a centrosymmetric structure. There is nothing there. But then what we did is that we have the band structure calculation, and then in those band structure calculation you can actually have the spin texture, and you can see the spin up, spin down texture is there. I think in the next work I will show more. So there is no proper splitting like a Rashba as you would expect, but there is a spin texture related splitting there. So we kind of coined it as a pseudo Rashba, and we fighted a lot with the reviewers. Somehow we got kind of convinced them that this makes also sense. So even if it's a CS2AGBI BR6 like a cubic structure, you can see pseudo Rashba effect there, and we also have the spin texture evidence for that. We have also done something. Yeah, I'll be fine. I'll be first anyway. So this is another thing where this is a hybrid perovskite material, like organic, inorganic perovskite material, and where you would like to see how the Rashba splitting is actually there. So this is not only for the inorganic, but it's also for the hybrid perovskite material that one can see that. Okay, so the last thing what I'll show is about the piezochromism or the pressure effect. So in principle, I mean, in the lab, in the synthesis lab, you cannot really synthesize all the materials that you would require to kind of see some kind of particular level of application. But you can always have this pressure parameter where you can also put in a uniaxial, biaxial, or hydrostatic way, so that you can actually achieve new phases, which could be really useful. And then there is a kind of, there is a doubt, and also that's a beauty in the same way, because people think that if you take out the pressure, it will be kind of probably going to that particular phase. It's not, because the diamond is the best example for that. It's a high pressure phase, but it still exists. So, I mean, the point is that you put as much as pressure as you can, keeping the dynamical stability level, the limit, and then you can actually achieve new materials with a new perspective there. So one can actually see that with this pressure. So this is one of the recent material that we have actually showed. I won't take much time on that. So this is a cerium tantalum nitride materials, where this is kind of a Rashba splitting system, where we can actually see how so you can actually see there is a splitting here in this conduction band and the valence band, and what we show is that, okay, why is coming like this? Anyway, so this is kind of a band structure with a pressure, with some amount of pressure where the structure is dynamically stable. Because whenever I show this kind of things, there is always question that if it's really dynamically stable, if there is a negative frequency, there is no frequency in that way. Then we have also calculated the spin texture from there, and we have actually calculated how the spin texture is actually changing. And this can be done for any experimental synthesis system. We can actually calculate the spin texture, and we can see how the spin texture is actually evolve with a pressure. That could be pressure, it's a hydrostatic pressure, that could be biaxial strain, that could be uniaxial strain, anything. So one can actually see how the spin orientation is actually there. And this is kind of the Rashba splitting value that one can calculate from that, and the spin texture which is there. So this is unpublished result. So hopefully we soon start bargaining with the reviewer to accept it. So let's see how it works. And if you want to read something on the perovskite at high pressure, these are the two kind of review article that we have written, one in Applied Physics Review and another is Materials Today. In the materials today, it's more extensive, where we have also seen not only the optical but also electronic, optical, and the magnetic properties for that matter. I'll just leave with the last thing, which is the neuromorphic. So I'm really interested to show this thing because it's something beautiful work has been going on, and there's a lot of things one can do. So if your perovskite synthesis material that you have synthesized, if doesn't work, please don't put it on the trash. You can see if that could work for a neuromorphic material, because there is a lot of potential with this material one can see. And the main way to see it is that one can see how the ion migration actually happens, and from there one can see if there is any possibility of neuromorphic computing, because your neuromorphic computing is the next big thing, because quantum computing, you cannot really create that low temperature to do some real application. Neuromorphic, you have to do with the classical, but in a way of neural-like network, where you have the calculation that you are doing and also the data that will kind of circulate. And perovskite material has been shown kind of quite good for that. So these are some of the endurance factor that we have done there. And this is how, I mean, one can see, and so any perovskite material one can see if there could be good for neuromorphic materials or not. And these are some of the other energy things I'm not showing. I mean, these are some of the catalysis things, so we kind of did some catalysis study also. So, but we are not showing those things, so I'll just conclude here. Oops, thanks.
Thank you very much. So one really small and short question. Otherwise,
yes.
A short question. You said you spent some time in trying to look in the haystack, so to say.
Sorry?
To try to look in the haystack. Try to search for materials which would be suitable, so to say,
right.
and not having that.
Yes.
What is the criteria you use there to
Yeah,
determine
so,
whether it's a promising one?
So basically, in the high throughput computing, kind of set up some criteria. I think when I'm showing this this high throughput computation for the perovskite materials, we set up some criteria about. So one of the first criteria is those structure needs to be stable, both dynamically and thermodynamically. The second criteria is the band gap. It has to be in the proper band gap region. The third is the band edges, where exactly the band edges could be. The effectiveness, as you were mentioning in your talk, that has to be in the optimum values of the perovskite, which particular application you would like to show, and then the optical response, if it's kind of showing in the visible range or not.
okay, so thank you again.
Thanks.
Now I request Dr. Carolyn to present the memento to Dr. Sudev.
Thank you. Okay, thank you.
So the next talk is the first of a young researcher, and I like to welcome Lokesh Vendra from the IIT Madras. And it's 10 minutes, 12 minutes, and questions are 3 to 5 minutes.
So good afternoon, everyone. So my name is Lokesh Vendra. I am working under Professor Ravi Kumar and also co-supervised by Professor Gurpreet Singh. So today I am going to giving my talk on precursor derived transition metal modified silicon oxycarbides for as an anode material for the lithium-ion batteries. So the outline of the presentation, first I will discuss about the energy storage devices and why PDC polymer derived ceramics are used materials for the lithium-ion batteries, and transition metal modified PDCs, my material synthesis process, material characterization and electrochemical testing, finally conclusions. So this is a schematic of transition metal modified silicon oxycarbide. So energy storage devices, we already know that CO2 emissions causes global warming. So the world is moving towards the green energy. So we are generating green energy, but we have to store in an efficient manner. For that, we require energy storage devices, which is used for the we can use in an efficient manner. So we have two types of energy storage devices: batteries and capacitors. So from this diagram plot, you can see batteries having high energy density and capacitors having high power density. So here I am targeted to improve the power density and maintaining the energy density as well as for the batteries by using the transition metal modified silicon oxycarbides as an anode materials in lithium-ion batteries. So literature about the, so I am skipping this because this is some introduction about the polymer derived ceramics. So here my work is mostly on the silicon oxycarbide polysiloxanes. So yesterday talk, Professor Dr. Sujit told that why we are using silicon polymer derived ceramics, the silicon oxycarbides as an anode materials in the lithium-ion batteries. So I am not going very deep, just I am telling the lithium storing mechanisms in the PDCs. What is the lithium storing mechanisms in PDCs? So there is still debate going on. There are two possible mechanisms in the PDCs how the lithium is going to store. The first one is the interstitial spaces and edges of this graphene layer, that is free carbon, and then the second mechanism is it may be going to the mixed units of SiOC units. From the literature, what we notice is that the performance of the electrochemical performance of this silicon oxycarbides as anode materials, it depends on the following factors like pyrolysis temperature, amorphous nature, and starting precursors, which they say the carbon content, and free carbon network. So if you have percolated carbon network in your SiOCs, so it will improve the conductivity. And high carbon content is an advantage, but it also disadvantage that it increases the irreversibility, and it should be porous structure. And also people are trying to incorporate some metals and metal oxides into this SiOC to improve the electrochemical performance of these anode materials. So transition metal modified silicon oxycarbide. So most of the research is explored for the structural applications. However, very few people are reported for the energy application. So my focus is on this niobium and titanium modified silicon oxycarbides for the energy applications. So this is my synthesis process. So my starting precursors are titanium tetra and butoxide, 1:1 volume ratio of polymethyl hydroxyloxanes for the synthesis of titanium modified SiOCs. Similarly, for the niobium, I am using the niobium ethoxide and polymethyl hydroxyloxane 1:1 volume ratio to get the niobium modified SiOC. We also synthesize the pure SiOC for comparison purpose. So this is the electrode and lithium coin cell preparation. So where I am using the active material 80% and 10% carbon black and VVDF 10%. So we are getting a honey-like paste. We are making the honey-like paste and applying on a copper foil by using Dr. Blade method, where after that we dried in a oven for overnight, and then we punched the copper electrodes in the required shape, and we make a coin cell in the argon seal glow box. So we perform the FTIR on the cross-linked powders of titanium modified silicon oxycarbide. There we notice that there is a new peak at 900 centimeter inverse. So this could be of SiO-Ti linkage. So the possible mechanism what we predict is forming of SiO-Ti linkages with the evolution of hydrocarbons. Similarly, for the niobium also, we observe a peak at around 924. It could be, so the possible reaction means what we predicted is, it's also forming a SiO-Nb linkage with the evolution of hydrocarbons. The phase evolution is performed on the pyrolyzed powders, that is at 900 degrees, and annealed powders at 1200 degrees. For the pure SiOC system, it's in amorphous state only. However, for the titanium modified, also it shows the amorphous nature. And but at annealed sample with slow scan, we found that after heat-well refinement, the conformation of the TIT crystallization in the annealed sample, but it is very not resolved in the high scanning rate. For the niobium, what we observed is the crystallization of the phases like NbO2, niobium carbide, and SiO2 for the annealed samples, and pyrolyzed sample shows amorphous only. So at higher temperatures, the possible reactions, what we assume it like this for the titanium modified SiOCs and for the niobium modified SiOCs. So the Raman analysis is also performed in order to confirm the presence of free carbon. So in all samples, pyrolyzed samples, in niobium and SiOCs, there is poor signals of DNG peaks because of the fluorescence. However, in case of titanium modified SiOC, we are getting the clear peaks of DNG peaks because of the more amount of carbon present in the titanium precursor. Similarly, for the annealed sample, we observed a clear peaks of DNG peaks, which represents the presence of free carbon in the form of DNG. So the TM microstructures of annealed SiOC shows a amorphous structure. It's confirmed from the SAD pattern also. And for the annealed titanium modified SiOC, where we high resolution microscope confirms the titanium despacing of titanium carbide crystals. Similarly, for the niobium modified annealed samples, we clearly observe the uniformly distributed crystals in SiOC matrix, and high resolution microscopes shows the despacing of SiO2, NbO2, and NBC, which well agreement with the XRD results. And the SAD pattern shows the polycrystalline nature of this material. So the XPS also we found in order to confirm the bonding nature. So where we noticed that in annealed sample there are more amount of SiO4 bonds. Similarly, so the respect to electrochemical performance of these anodes is shown here. So because of no free carbon available, so it shows very low values at a pyrolyzed sample of pure SiOC. However, annealed sample from the Raman spectroscopy, you can find that there is a availability of free carbon in the form of DNG peak, and it shows a values of around 500, and the first cycle efficiency is 43%. So what we assume is that the more amount of SiO4 causes the irreversibility, increase the irreversibility, and the reversible phases, what we are in presence of free carbon. So coming to the titanium modified silicon oxycarbide, here similarly the SiO4 bonds, SiO2 bonds are more in annealed samples and compared with the pyrolyzed one, and also we have TIC bonds are more from the deconvoluted peaks of the XPS. So it confirms that titanium carbide is formed in case of annealed sample, and there are more number of SiO4 bonds. So the electrochemical performance of the titanium modified SiOCs anodes shows a low efficiencies. It might be because of at less than 1000 degrees, this SiOC is more reactive towards the lithium and forming irreversible pages. Similarly, for the annealed sample, the reversible sites, what we concluded that the disorder carbon, which conforms on Raman, as well as SaCO3 or SC2, which forms a reversible phase, which is confirmed from the XPS results. And also there is a high conductive carbon, which is causes for the improvement in the first cycle efficiency of these annealed samples. And for the niobium modified, so here also we have observed the more amount of these SiO4 bonds, and there is a decrement in the NbO1, that is because of the formation of niobium carbide. So the electrochemical performance of these niobium modified SiOCs, which shows very low values when compared with the titanium modified SiOCs. This could be because of the precursor itself having less carbon when you compare with the titanium precursor, and also the forming of this insulating phases, which obstacles for the lithium diffusion, and there is a less amount of availability of the free carbon. So all these factors making into low values of charge storage capacity. So conclusions. So first time we evaluated the electrochemical performance of the titanium modified and niobium modified silicon oxycarbides as anodes in the lithium ion batteries. So the presence of the dominated phases of SiO4 which causes a more irreversibility in the samples, as well as the free carbon and titanium carbide which improves the improves the conductivity, thereby the first cycle reversibility increased in the annealed titanium modified silicon samples. However, the annealing also has some effects resulting in the formation of this insulating phases which causes structural stability, also obstacles for the lithium ion diffusion. So what we concluded is the pyrolized sample of titanium modified SiOC which performs better after 100 cycles also, it's showing some 250 after 100 cycles, 250 capacity milliampere hours per gram capacity after 100 cycles also. Remaining samples is not performing that much. So the pyrolized sample performs better because of this free carbon is encapsulated in your amorphous transition metal modified SiOC structure. So this is the schematic. What we assume is, so here these graphite layers are supported by this amorphous transition metal modified SiOC structure, but for annealing this this carbon is reacting with your transition metal and forming in carbides, thereby the loses structurality. That's why we are getting poor cyclic stability. So thank you. So we already published this titanium modified paper, and we are ready to submit the niobium modified SiOC paper. So thanks to Shakir, which helped me in making battery cells and also testing, and I thank the University of Kansas Charles for trying, and I also thank the Office of the Global Engagement for the travel grants for the USA, and also thank for the NSF and CTFM. So this is everything. Thank you, everyone.
Thank you very much. So I think we have a question.
Thank you for presentation. Okay. Thank you for your presentation. Interesting work. So I just have a question about niobium. It's quite heavy elements, and I guess the theoretical capacity may be lower than the silicon oxide carbide. So what benefits of niobium, and you're targeting material niobium oxide or niobium in the final composition?
Actually, niobium we selected because of this the voltage window, potential voltage window for the niobium. The pure niobium will be more, so it avoids the lithium segregation. So it's the main problem in the lithium ion batteries. So at low voltages, it causes of lithium segregation. So if you use niobium as an anode, so the voltage window will expand. It's at 1 volt. The niobium starts lithiation of this lithium ions into niobium structure at 1 voltage, 1.1 around. So it will avoid the lithium ion segregation. So that's why we selected the niobium precursor, starting precursor to modify the SiOC structure.
Okay, and your final target was.
But we are ending up with the different crystal structures, phase evolutions. So it insulating phases in SiOC matrix, which causes the obstacles for the lithium ion diffusion.
Okay, thanks.
So this is first time we are working, so we are still have to improve the performance of these materials.
Okay, one last question.
Hello. Thanks for the presentation. I have a doubt that how do you make sure the same amount of free carbon can present in each sample, because it is the one which is giving the most amount of electricity in your system.
I didn't get.
How do you make sure the same amount of free carbon present in every sample?
No, it's not the same amount. I didn't mention same amount. Starting precursor decides the amount of carbon. So you can see for the so titanium, the precursor tetrablue oxide, we have lot of carbon is there. But in case of niobium, the carbon is less. So that's why the final carbon, the final product, the carbon is less in case of niobium, but is more in case of titanium. So we have to quantify the free carbon for the pyrolized and annealed samples. So here I didn't mention what is the amount of the free carbon in my samples. So I am telling from the precursor itself.
Okay. It depends on precursor.
Yes.
Thank you.
Yeah, precursor matters.
Okay, thank you very much, Lokesh, for this nice presentation.
I now request Dr. Carolyn to present the memento to Mr. Lokesh.
Sorry. Thank you. Thank you.
And now we will have the last presentation before lunch, and it's held by Jan Felix Wendel. He's a PhD student at the University of Bayreuth, and he will present his PhD topic about PDC-derived ceramics and the physical vapor deposition.
So can everybody hear me? Yes. A small correction, it's not my PhD topic, but I want to give you today a small overview about a part of my project I worked on. And the topic is the combination of polymer-derived ceramic and physical vapor deposition coating methods for new functional coatings. In the beginning, I want to lose some words about the motivation to this project. On the one hand side, there is the polymer-derived ceramic technique. This technique is usually and often used for the production of oxidation protection coatings. And one advantage of this technique, beside that it is a very versatile and easily tailorable technique, is that high coating thicknesses can be achieved. It's about a maximum of 100 microns. On the other side, the mechanical properties of such coatings are, compared to other coating techniques, are relatively low, for example, in terms of abrasion resistance. On the other hand, there is the physical vapor deposition technique. With this technique, thin but hard coatings are produced, which makes them favorable for wear protection applications. And as you can see here, the properties of both techniques are kind of contrary. So there was the idea to combine both coatings to get the best of two worlds in one coating system. That means the mechanical properties of the PVD side and the high thickness and therefore a good oxidation protection property of the PDC side. To reach this goal, we have to answer mainly two questions. First, if it's in principle possible to combine both coating systems in one coating, and which parameters do we have to use, under which conditions we can succeed this. And second, if there is a synergistic effect by the combination. And in this talk, I want to focus on the mechanical properties of the combined coatings. To answer these questions, we followed the strategy to first start with an easy and unfilled PDC coating system to identify proper process parameters, and then transfer the gained knowledge to a filled and therefore thick PDC system. The materials we used is for a substrate stainless steel. This was dip coated in the silicene with the silicene precursor Duracane 2250, which chemical structure is given here. This coating was cross-linked in air at a temperature of 110 degrees Celsius and subsequently PVD coated with a titanium nitride coating at the temperature of 370 degrees Celsius. With this parameter set, we resulted in a surface coating looking like this. You can see it in the SEM picture here. The coating was highly spelled, and fragments of titanium nitride and also the Duracane coating were visible at the surface. The reason for this spelling is the release of some gaseous species from the Duracane coating. To understand this, we can have a short look at the TG curve of the precursor. The pre-treatment temperature was about 110 degrees, and the process temperature of the PVD process was about 400 degrees Celsius. So the biggest amount of the mass loss happens within the PVD process. This results in this release of gases. To avoid this, we changed the pretreatment temperature to 700 degrees Celsius, and therefore the PDC coating was completely ceramized and no more release of gases was possible during the PVD process. With this adapted pretreatment temperature, we resulted in a coating morphology which was homogeneous and without spalling, like you can see it in both SEM pictures on the left-hand side. The system consisted of a 800 nanometer thick duracell coating and also an about 800 nanometer thick titanium nitride PVD coating. The titanium nitride growed in the 111 direction preferentially, which is a very typical orientation for PVD processes, which occurs in PVD processes, and it's also favorable for wear protection applications. Now, I would like to have a short look at the mechanical properties of the systems. The table gives some values of the, is it working? Yeah, of the combined coating and also of both single coatings for comparison. In terms of hardness, which was a nano indentation measurement, we can see that stainless steel has the lowest value and the combined system the highest. This shows that there is a synergistic effect by combining both techniques. What I have to mention is that you cannot see this in this system in the pull-off adhesion. Here the combined system shows the lowest value. This is because of the formation of a glassy layer on the surface of the duracell coating during the pretreatment at 700 degrees Celsius. And to this glassy layer, the titanium bond coat of the PVD coating is low adherent. But an also interesting property is the scratch resistance. Here you can see light microscopy images at different forces in the scratch test. And the titanium nitride coating fails at values lower than 2 Newton, and the duracell coating at about 5 Newton. The reason for the failure at low values is the so-called axial effect, which says that thin and comparable hard coating on a comparable soft substrate cannot withstand high loads. In contrast to that, the combined coating shows forces higher than 10 Newton or about 10 Newton. This increase in scratch resistance has its reason in the layered structure of this coating system, because the hard titanium nitride layer at the top is the hardness of the titanium nitride layer on the top to the soft substrate is mediated by the PDC system. And therefore, this axial effect could be reduced. Now, I would like to have a look at the second step, the filled systems. Here, we investigated a system which consists of a bond coat and an about 25 micron thick top coat. This top coat is produced from the duracell 1800 precursor and 2 different ceramic fillers. The top coat was pyrolyzed in air at a temperature of 1000 degrees Celsius, and again subsequently PVD coated with titanium nitride. Here I just want to give you an idea of the mechanical properties in terms of pull-off adhesion. Both coating systems, the single and the combined coating system, show the same value. And I have to mention that the failure in this adhesion test occurs within the PDC coating. That means that the adhesion of the titanium nitride coating is higher than the given about 21 MPa. And we investigated also the crosscut tape test and found a significant increase in the damaged area as you can see it here in the both pictures. So here in this combined system, there's also an increase in mechanical properties. We also find an increase in scratch resistance, but because of the time, I would skip this. And yeah, then I would come to the end. And as a conclusion of this short overview, I want to answer the questions I asked in the beginning. First, if the combination is possible, the answer is yes, it is possible, but we have to ensure that no gases can be released during the PVD process. And one possibility to do this is the caramelization of the PDC coating before that. And the second question was about the synergistic effect in terms of mechanical properties. And the answer here is also yes. We found an increase in hardness, scratch resistance, and cross-cut tap test for both a thin and also a thick PDC coating. To conclude this, we can keep in mind that with the combination of different coating techniques, we have the possibility to produce coatings with an extended profile of property we could not cover with a single coating system alone. In the end, I would like to thank the Federal Ministry of Economic Affairs and Climate Action for the financial support of this project, and Dr. Tangaman Garg, Dr. Lenz Leite, Dr. Mucha, and the group of Professor Ravi Kumar for the support and the contribution to this project. And thank you for your attention.
Thank you very much. Are there any questions?
Yeah, first of all, thank you very much for your nice explanation on the PDC and PVD coating. What do you think, what is your, how do you maintain the surface roughness? Because when you are doing applying the PDC coating, it will be certainly porous, right? You cannot get a very compact coating on the substrate. Now, when you apply the PVD coating, it will be uniformly distributed throughout. So we'll have the surface texture issue on the top. How did you overcome that?
So roughness, if I got the question correctly, you asked about the roughness and how it affects the PVD coating. It plays a certain role. Yes, the adhesion it affects, definitely, of the PVD coating. We saw it in the first example with the thin coating, which was quite dense. And their adhesion was reduced because the surface was quite flat. And in the second example, with the filled system, the coating surface is a bit more rough, and the adhesion was increased. When there is too much porosity, it will definitely have a negative effect. So you have to avoid too much porosity in the PDC coating at the surface. And but it also has a positive effect. Combination of both techniques and adjusting both techniques is important.
Okay, so thank you very much for this nice talk.
Thank you.
I think we are finished for this session. Thank you very much for your attention.
I request Dr. Caroline to present the memento to Mr. Yang.
Dankeschön.
Now I request Professor Ravi Kumar to give the memento to our session chair, Dr. Caroline Sitzman. Now we have a break, lunch break. I request everyone to be back here by 1:25 as we will sharply start at 1:30. Thank you.
bonds to the unstable solid electrode interfaces. And so why it is happening? Who is making the problem in the first phase, like that first cycle loss? As we always say, for the polymer derived ceramic energy application, the second cycle is the first cycle for us. Like always we lost lithium in the first cycle. So to understand that, obviously in the same line that most of my colleagues have worked on, I have also etched out the silicon oxycarbide, tried to etch out the silicon oxycarbide. And I was expecting that if silicon oxycarbide is creating problem with the lithium loss in the first cycle, I should have an improvement in now. But to my dismay, it was not happening like that. In fact, when I etched out the silicon oxycarbide, both the capacity have come down and except in the case of BMV that I'm not investigated further on that system. But in general, if you can see that the silicon content has come down for all the systems, but along with that the capacity and first cycle loss also. So what this means that the capacity towards capacity, there is contribution both from the silicon nano domains and also from the graphitic layers on that. And so I have selected actually basically that methyl system for my obviously for my studies, because it has shown a good specific capacity values. Inside that methyl system, I have done on study on thinking that these nano domains are actually creating these results what I am getting, not the carbon content alone. If it has been carbon content, then I should have got a better property for phenyl system. That's not the case. So I have, in order to confirm that, I have done the studies under 3 different temperatures. The same ceramic conversion was carried out at 900, 1200, and 1500. This 900 degrees Celsius is an extreme case where you have just completed your pyrolysis. Maybe that structures have not come, there are still good amount of dangling bonds there, the graphitic domains might not have come. The study is still on in the term analysis we have to do and confirm that, but still what we feel is that at 900 degrees Celsius when we tested there was no voltage pickup, obviously because of the conductivity issue, and the conductivity issue is related to the non-formation of a very good phase separated graphitic layer there. In the other extreme, if you go 1500 when I heat treat, the issue was that silicon carbide will start forming. Crystallization will happen by the exchange mechanism particularly. If you move a little bit more, that carbothermic reduction will also happen. So my silicon and carbon are being used for the formation of silicon carbide that I don't want. So whenever that is being happening, there is appreciable decrease in the amount of carbon in the system. There also the voltage pickup was low. So the intermediate temperature between 1000 to 1400, maybe I have focused on 1200. There I have a good spectrum of nano domains, good amount of silica, good amount of carbon in that, which can be useful for my study. So I am pursuing with that right now. So in brief, right now the study is in progress and we have the silicon boron oxycarbide materials being explored for the lithium storage, and we have been happy with the results so far. And we have found that both carbon and SO domains should be contributing towards capacity. And more than the carbon content, the actual morphology of the nano domains, the nano level morphology, or how it is distributed, to what level. So that will have an influence on that. So I'll just briefly go through the other side also, that next work what we are doing is for supercapacitors. You're knowing supercapacitors are for the high power for short duration applications, and carbide derived carbons are the materials for that. And my idea was to have a polymer derived silicon carbide which will have some porosity distribution in the mesophase or macro phase, and I will incorporate the micro level porosity by etching of the silicon from that. So this is a carbide derived carbon with a hierarchical porosity. So far we have been collaborating with CMET Hyderabad for this particular work, and we could get a carbide derived carbon material. We are still working on to solve some issues on chlorine content, and because we are using chlorine for etching, the chlorine content is relatively high. So in order to keeping up with the momentum of the work that we have been doing right now on carbide derived carbon for supercapacitors and SiBOC for lithium ion cells, right now we are initiated some work on the modeling. So it should ease up my work, the right composition for my electrode application I should get. And I am also working on the micro lattice or fiber SiBOC right, in near future. And the Mexine is another thing what we will be looking into. So for the micro lattice 3D printing and all, We have been working on a cross-linkable UV curable polysiloxane resins that we have been right now synthesized. The work is right now on. Max phase materials, we have developed the max phase materials as a precursor of mexines. Mexines are offering very good potential, particularly with respect to sodium and potassium ion batteries for the future. So this work is already initiated. So the momentum we are keeping up with the development in these areas. So the future is for 3 types of power systems that I am focusing on right now. Is for powering the spacecraft, so longer journeys, powering the surface systems on extraterrestrial planets, and powering the extravehicular activities. In these aspects, when we have a thought process in that, the 2 technologies have caught my attention, like it's very much important, like the MIT's report on flexible fiber, batteries as a fiber, as a rope or something, and flexible batteries. This could lead us to a wearable battery for the spacesuit application. So this is an area that in immediate future we will be focusing on. Next thing is a structural battery, like the battery itself becoming the structural component of the body of the vehicle, like the cars, or in our case it's the space vehicles. So these 2 aspects are the future that we are foreseeing, particularly with respect to the polymer derived ceramic materials. Fabrication will not be a much problem, but optimization we have to do little bit hard work. So the concluding remarks, I would like to end my talk with this message for you to take home. For sustainable space habitats, we should have more efficient and safer energy storage systems. The demisability is another aspect that you have been talking right now. I don't have much time for that. So you can check, Google it. Second thing is that the evolvable material systems and sustainable manufacturing methods, that's the next aspect of the work that we have to do it in future. And the polymer derived ceramics, we hope and we believe that can support to reach those goals. And I have this particular work was possible. All this work are being carried out ceramic metrics products division of IGSTC, where Dr. Ranjit is heading us. And I'm thankful to him for the support. And Srimati Sujata is heading the energy system division. They are making the batteries and all. And I'm thankful for my group directors, my deputy directors, and director, Dr. Sunnikishan Nair, for the support. And I have my project collaborators outside my VSSC, like CMET Hyderabad and NET Jalandhar. And inside VSSC, our most favorite analytic and spectroscopy division, they are doing all the analysis for us. And the energy system division is doing all the battery making. And this is my team members in CMPD and ESTD. And this is our Dr. Vikram Sarafai, who's the father of our space program, and he has made this very comment that the nurturing research is like planting a tree. And particularly with respect to the polymer derived ceramics, we have seen for the last few years that the tree has grown. Now we have to sell the fruits. So maybe it's time for that. Thank you. Thank you.
Thank you very much. We have time for one short question and one short answer. Yes, yes. Yeah. As you want. Microphone decides.
Hello. Thank you, sir. Thank you for this lecture. So I would like to know what is the concentration of boron in SiBOC system?
Right now we have optimized it up to 4% boron.
Okay. So if you have boron in such low concentration, whether it affects the dispersion where we have shown 900, 1200 and 1500.
Mm-hmm.
You're talking about 1200 is the best like you get SiO, SiC system. So whether you need a pure SiOC system or you need a SiBOC system, which one will be better?
1200 will be a pure SiBOC system where it's a glassy phase with some microcrystals. So SiC starts forming, but it's not that much a big problem. But it's not an SiOC system anyway. The boron is not going out of the system during that system. We have already proved that in our earlier studies and papers. Boron is incorporated into the system. So it is an SiBOC system at 1200.
Okay. Thank you.
Thank you very much.
Yeah.
Thank you, sir. I request Dr. Oliver to present memento to Dr. K. Srijit.
Now I hope it will work. So Dr. Tada. So please.
Good afternoon, everyone. First of all, I'm so sorry for taking time to prepare my slide. And my name is Shota Dada. I'm recently joined to IIT MADRAS as a young international faculty. And before coming to India, I belonged to the Professor Yuji Iwamoto's laboratory in Nagoya Institute of Technology, Japan. So today, I'd like to talk about my recent research work based on the conducted in Japan. So the title is In situ formation of nanometer size nickel indium nitride antiperovskite type nickel indium nitride crystallized embedded within amorphous silicon nitride through synthesized through the polymer derived ceramics route. So here is the outline that I want to talk. First, I'd like to briefly introduce the recent advantages of polymer-derived transition metal silicon-based non-oxide nanocomposite. I will explain about this on some kinds of the catalytic applications. And then I will firstly demonstrate the in situ growth of antiperovskite nitride. In this case, nickel indium nitride, which is embedded in amorphous silicon nitride matrix. So, and then I will discuss for the in situ compositing behavior for this titled compounds. And then I will demonstrate the functionality of this material, that is CO2 adsorption and desorption behavior this time. So here you can see, as you know, the polymer-derived ceramics is extensively used in terms of their great processability, thermal and chemical stability. And recently, these excellent properties extended to the field of the heterogeneous catalysis. The polymer-derived metal, transition metal silicon carbon nitride, transition metal silicon oxycarbon carbide nanocomposite is developed as a robust and reusable heterogeneous catalyst in various chemical reactions, including the kind of the harsh conditions. And in this field, there's lots of research, great research is conducted by the Dr. Günther Motz and also Red Kemper. And so it stands on their part of their contributions. So here is an example of the composite materials. As you can see, it's cobalt silicon carbon nitride. To synthesize this composite material, we typically use these silicon-based oxide or non-oxide polymer. For example, in this case, polysirazine, and then this polymer is chemically modified with metal sources, and then it's pyrolyzed to afford this composite material. So it's very simple synthetic strategy. And then this composite is very stable chemically and also thermally. And so we can use this composite material for various type of catalytic reaction. For example, in this case, the chemoselective hydrogenation reactions. Also, this type of heterogeneous catalyst can apply by changing the type of metals. For example, the hydrogenation of the organic compounds, the hydrogenative condensation, and also the hydrogenations. Also, we can apply to for example, the gas phase reactions such as CO2 methanation, and so on and so on. Yeah, so this is recently extended the PDCs to the heterogeneous catalysts. And also, recently in our laboratory, we have developed the transition metal and the amorphous silicon nitride nanocomposite via the PDC route. Here you can see we synthesized the cobalt-modified polysilicon. It's cobalt coordinated polysilicon, and then it's this polarized to the to transform the metal cobalt amorphous silicon nanocomposite samples. So the interesting is that the nucleation of metal species is proceeded at very low temperatures, which is governed by the in situ formation of nickel, cobalt, in this case cobalt nitrile phase, and then it decomposes to the metallic cobalt. So this inducing the nanocompositing of this material. So this is a very simple reaction, just mixing with the precursor polysilicon, for example, and the metal sources, and then react, and subsequently this polarize it. So by using this simple synthetic method, in this case, I aim to synthesize the dual metal type or multi-metal type silicon-based composite system. And in this case, I will be focusing on the synthesis of the anti-perovskite nitride and silicon-based composite material. So as you may know, this anti-perovskite means that it's similar crystalline structure with perovskite, but it's electrically inverted. So this is this kind of material is greatly studied and exhibiting very unique functionalities such as ionic conductivity, negative thermal expansion properties, and so on and so on. But the problem is that most of the reported functionality is that the anti-perovskite mostly it's the bulk shape or micron-sized powders. So in this case, by using this PDC route, I tried to synthesize a nanometer-sized nanoparticle embedded within the amorphous silicon nitride matrix. So the objective is that in this case, first demonstration of in situ nanocompositing of this composite, and I will show you the functionality of theoretical absorption and desorption property. And also we checked the properties of the ammonia synthesis by through the chemical looping protocol. But in this case, I would like to skip this. Yeah, here's a synthetic route used in this study. As I said, the synthetic route is very simple. We just add the metal source, in this case nickel chloride and indium chloride, into the polysilicon solution, and then those reflux for 15 hours under inert atmosphere to for the single source precursors for the of the nickel and indium modified polysilicon. And also we used in this study we used two types of polymer, which is the polyhedral polysilicon, it's so-called PHPS, and also we used polybinary metal conventional silicon, which is so-called HTT 1800. And the difference of the nanocompositing will be discussed. So here, this is the FTIR spectra that I want to confirm the chemical reaction between the metal sources and polysilicon. And as you can see, there's slight difference between the as received polysilicon and the metal modified polysilicon. And if you look at the the PHPS-based system, we can see the reduction of the NH group and SIH group in intensity. And also we can identify the additional peaks assigned to the ammonium chloride. So, and in contrast to the PHPS-based system, if we look at the HTT 1800-based system, we can just identify the reduction of the NH groups and also the SIH group in intensity. So to explain such phenomena, in our previous research, we discussed the possible reaction between the nickel chloride and the polystyrene, which is the transition metal catalyzed dehydrocoupling reaction. For this reaction, we can afford, so by using these reactions, the NH groups and the SH group reacted to afford the ternary serial amino groups. And this reaction was catalyzed by nickel chloride. And then the nickel chloride was coordinated to the in situ form, the ternary serial amino groups to give the nickel 2+ complex. As in this case, we can identify the reduction of the NH groups and the SH groups. So we expect it to occur such reactions. And then if we want to think about the reaction between the polystyrene with the indium chloride, in this case, there's a difference between the type of the polystyrene. We can also just identify this peak assigned to the ammonium chloride when we just modified with enzyme chloride and also nickel chloride. And this peak is not identified in this system. So we assume that the following reactions, that is the acid-base reaction with SiNH SI group with indium chloride to afford the indium nitride bond with hydrochloric acid as a byproduct. And if you're thinking about the FDR spectra, in HTT 1800, the indium chloride will not react with HTT 1800 directly, mostly due to the presence of the vinyl groups and the methyl groups, which have the highly strict hindrance. So we assume that in this case, the indium chloride is weakly coordinated with the polystyrene. And also, if we're thinking of to generating the ammonium chloride, we think that another reaction, which is a metal catalyzed transamination reaction. And the transamination reaction proceeds this as shown here, and this produces ammonia during the reaction. But as you may know, this transamination reaction will proceed more high temperatures. For example, it's over 250 degrees C. So as we assume that this reaction was catalyzed by the metal chloride. So to confirm these suggestions, we measured TG. We monitored TG curves of the indium modified PHPS and the indium modified HTT 1800 under inert atmosphere to 1000 degrees C. And here is the result. And if you look at the PHPS based system, the indium modified PHPS exhibited higher thermic yield than the as received PHPS, which resulting from the formation of the indium nitride linkage. which means the polysilicon is highly cross-linked during the synthesis. And also, we can identify the continuous weight loss over 550 degrees C, which is consistent with the decomposition reaction of the indium nitride in inert atmosphere. So we confirm that the suggestions that in PHPS system are forming the kind of the highly cross-linked structures. And then, in contrast, the PHPS-based system, if we look at the HCT 800 system, there's a significant weight loss at over 350 degrees C in indium chloride modified HCT 800 samples. So this is due to the evaporation of the indium chloride at the 300 degrees C. And so, yeah, we confirm that the proposed the structure of the for the reaction between the indium chloride and polysilicon. And we assume that this difference is affecting to the nanocompositing for the nickel indium antiperovskite nickel indium nitride. Yeah, and also maybe we can summarize this reaction, but we will skip to save the time. But one thing I want to mention that the formation of the nickel 2+ complex is very important. And in previous study, we discussed that in situ formation of the nickel nanoparticle via the SN2 type reaction and following the nickel nitride formation. And then subsequently, this nickel nitride species were reduced to the nickel nanoparticles. So this is very important. We can identify the presence of such kind of the complex. So we assume that the nickel crystallization will occur in these systems. So here is the patterns for the nickel chloride and the indium chloride co-modified polysilicon. And as you can see here, the very broad peak was appeared for the PHPS-based system at when the polarized at 300 degrees C, which is assigned to the nickel FCC nickel. So this result showed that the in situ growth of the nickel nanoparticle occurred first, and then by increasing the polarized temperatures, this peak is decreasing consistently, and then the new peak has appeared, which is assigned to the antiperovskite nickel indium nitride. So we assume that, yeah, and we confirm that the in situ formed nickel nanoparticles has been converted into the antiperovskite phase. But as you can see here, we can see some difference when we look at the HCT 800 system. We can identify the nickel antiperovskite system even at 300 degrees C. So this system is, the antiperovskite was formed in situ formed more easier due to the the diffusivity difference of the indium species. So time is coming, so I will skip some slides. But if we carefully control the chemical composition of this system, we can make a single-phase nickel antiperovskite nickel indium nitride and amorphous silicon nitride composite. And yeah, here's a TEM observation. As you can see, if you look at the PHPS-based system, it's the metal nanoparticle is highly dispersed. And in contrast, the HTT system exhibiting the agglometric structure, which is due to the, maybe it's also explained by the diffusivity of the indium species. And the interesting is that if you look, it's a nitrogen adsorption and desorption measurement to characterize the texture property of this composite sample. As you can see, the micro and mesoporosity were formed in the HTT-based system. So we think that this formation of the micro and mesoporosity is due to the enzyme chlorides worked as the inorganic template. And yeah, briefly talk. I will briefly explain about the functionality. And we can check the electronic structure, bonding structure of the composite sample by XPS spectra. And if you look at the XPS spectra of the composite sample and the bulk samples, the peak is slightly shifted towards the higher binding energy, which means the presence of the positively charged nuclear species. So I will test the interaction between the small molecules such as the carbon dioxide with nanocomposite has been tested. Yeah. And this is a CO2 TPD spectra confirming the unique CO2 affinity of these composite samples. As you can see, if we compare to this non-doped amorphous silicon nitride, which is a microporous samples, this interaction is explaining the CO2 physisorption. But if you look at this composite sample, the peak is consistently increasing with the CO2 treatment temperature is to be high. So that means the interaction is remained even at high temperatures. So we confirm the CO2 affinity on these samples. So for future, this is summary of my research. And for future aspect, this is actually ongoing project. So I will try to measure the CO2 conversion behavior on these samples. And also we try to make another system by using the anesometers, amorphous silicon nitride composite for catalysts, for future heterogeneous catalysts. And thank you for your kind attention.
Thank you very much. In sake of time, I will give you directly the present.
Okay. Yeah. If you have any questions, please ask after. Thank you.
With this, we conclude the session. I request Dr. Günther sir to present memento to Dr. Oliver.
Yeah.
I now request Dr. Ravikumar to take over the session, coming session.
So as informed earlier, Professor Silke Christiansen is not here, and we are advancing the panel discussion in that slot. As you may all have heard, Shri Madan, Director of IGSTC's talk, one of the reasons why we conduct such a workshop is also to clearly outline and define the outcomes of such a workshop. And in that context, IGSTC also focuses quite a bit on translational research and to see how such an interaction between two countries, India and Germany, on a particular topic can lead to some substantial output, and we need to clearly outline those outcomes. So in that context, we all know, many of us have been working in the area of precursor-derived ceramics for quite some time. And we also know that there are a few companies, we all know there are some companies which produces precursors and so on. But it is also clear to us that there are not many companies. The companies that you find which can make such precursors and so on are limited. So this panel discussion primarily tries to see where are we in terms of research on the lab scale, and at the same time, how do we move forward as far as commercialization of such precursors and precursor-derived ceramics are concerned. So in that context, we have few people, both from the industry as well as from academia. I would like to invite my the other panelist, Dr. Günther Motz, to also come on stage. I would like to invite Dr. Samuel Bernard, who is an academician from the National Lab. He's the director of CNRS, one of the labs in the University of Limoges. I would like to invite Professor Sanjay Mathur, who is from the Institute of Inorganic Chemistry from University of Cologne. Dr. Madhusudana, he is the general manager for Ceramic Technological Institute in BHEL. He's from the company, so he brings a different perspective. I am also pleased to invite Dr. Jürgen Mertes. He is head of printing chemicals from the company Merck. Dr. Lalit Kumar Sharma, he has been the president of the Indian Ceramic Society and also chairperson of the India chapter of the American Ceramic Society. I would like to invite Mr. Lalit Kumar Sharma as well onto the stage. And last but not the least, Dr. Ranjit Devasia, who has been leading one of the programs at Vikram Sarabhai Space Center, is also invited on stage. Please do come on stage.
Only 1 minute.
Sorry, it just fell down.
I hope we believe that this should not take more than 30 minutes. So we would like to hear the perspectives from both from academia as well as national labs and industries.
You have 1 more. Only 2.
Yeah. So I think we can straight away get started without wasting any more time. I would like to hand over the mic to Günther. So he has possibly a few questions to get this discussion started.
Yeah, the topic is what is the future of the PDCs, and therefore we have also guests from the companies, because research without companies makes no sense, and the research was for nothing. And therefore I have questions to the companies. What do you think, what are the future applications for the precursors? And do you have ideas what the research can do to enhance the development of precursors and the production of precursors also in the industry, to have a better commercialization? For the siloxanes, it's not a problem, but the number of siloxanes and especially carboxylanes is limited, and the interest is rapidly growing. And therefore, I would give the microphone to the colleagues from industry.
You can get started.
Yeah, good afternoon. And myself, Madhusudan. I come from a company, BHEL. It's in the energy sector. We manufacture power plants. More than 70% of energy produced in India is by the equipments made by us. We are working both in traditional, conventional energy sector as well as renewable energies. My lab is working on materials, ceramic materials, basically, and also new energy materials. So our mandate is to take the technology from lab level to upscale it to commercial level, so that we can commercialize the technology which is available now. So we collaborate with institutes, both in India and abroad, including ISRO. So we are also looking for more collaboration in the new energy materials like hydrogen, fuel cells, energy storage, etc. So my experience during the last 3 decades, mainly in the upscaling of technologies, I have in ceramic, mainly ceramic. A lot of challenges we have seen. I think I'll just share a few of things. I think most of the things are applicable to polymer-derived ceramics also. So first and foremost, what I feel is the availability of raw material. That is one of the challenge which we need to address first, especially when you deal with the polymer-derived ceramics, because you need to have a right precursor. Quality, not only quality, you need to have a quantity also, because most of the such a precursors available in the lab level in a small scale. And of course, finally price. As an industry, finally looking for the right price. So raw material is one of the issues. I'm very happy to see that your startup company, they are displayed some of the quantities of the chemicals. Of course, this is the first step in India. Not only India, in fact, today's speaker, Professor Gurpreet, mentioned that in US also it is very difficult to get the right raw material. So that is one area we need to focus more on this. And the second aspect is the safety aspects of these materials. When you deal with these chemicals, safety, not only when you deal with the chemicals, then the outcome of the process, like with the exhaust gases or chemicals, both liquid waste or solid waste or gaseous emissions, we need to see so that what type of regulations we don't know now, because even such industries, the type of regulation may be slightly different. So we need to see that what technology we need to have that. Maybe one of the solution is maybe the circular economy, so we need to reduce or reuse, recycle. So I don't know whether, even ceramic it is not very much implemented. So precursor derived ceramics, maybe we can think of implementing that from beginning. So overall, what I'd like to say that we need to consider manufacturing readiness level of these technologies, not only technology readiness level, so that industries can come forward and take this to commercial level. These are my initial thoughts. Thank you so much.
Again, Mattis can now continue because he is also from the industry.
Okay, hello, my name is Jürgen Mattis. I'm from Merck, and just by chance, 100% of the organopolysilizanes are produced in India and in an own company, so it's a Merck facility. And the availability of the material is, in principle, no problem. What we see is that over 90% of the material is not going to ceramic applications, it's going more or less into the coating industry. And this is, let's say, another focus. The point is we have an established set of products which is mainly designed for the coating industry. And if there are coming up some new applications, some new ideas also here from the group, we have to think about how to modify our products in the right way. And the main benefit here is to get some ideas, to make connects to people who are dealing with industries we are not in so far. And if there are some ideas of new structures which might be more feasible for certain applications and processes, we are also open to think about it. Because we are here in India, we have a very flexible team. It's a site who is only dealing with polysiloxanes, nothing else. Very experienced people, and we can do, let's say, some special chemistry, some special materials for special purposes. And that's the offer we can make. As always, we have to check and have to prove the business model behind. So 10 kg of a material to make is much too expensive, but if we are talking about a certain volume, that should be feasible. So that's, let's say, the statement of Merck. We are in the PHPS and also in the organic polysiloxanes. We have a set of materials. We are supporting potential customers and already our existing base. We stay to and we think about this technical, let's say, potential of the chemicals, and it makes it very interesting to work in that field.
Dr. Can I ask you one question?
Sure.
Your company also produces these precursors in India, is what you said.
Right.
Your company is not an Indian company. So, but you are producing precursors in India. But do you have any restrictions on what kind of precursors can be produced in India because of the dual nature of the kind of precursors which can also go for strategic applications and so on?
You
Do you have a company policy that that restricts a certain class of precursors to be produced?
For sure. We have these dual use restrictions worldwide, so there are some countries we cannot deliver the materials because of the silicon nitride formation, and you know silicon nitride is also used for weapons, so our policy is very strict. We do not deliver such products to any suspicious countries, I would say. Yeah. But the production itself is not restricted. No.
Okay. Thank you.
Welcome.
Good evening. I am Dr. L.K. Sharma. I was in CSIR. Now I am, after leaving that, now I am the CEO of one Mahamna Ceramic Development Organization. So when all these lectures were going on, so it was new field. So I was trying to compare all this with what we have learned in the past for ceramics. So I was comparing then when sometimes we used to have that some critical shape, all that. So we used to think that, okay, we'll make it by slip casting. When we used to do sintering, we want to get good density, then there we used to talk about additives. So all this was going on. So I would like to thank all the organizers for organizing such a dedicated conference on this subject. So I was talking to Ravi that what we have to speak, all that, new field, new questions. So when this thing came up, then slip cast, a lot of benefits, uniform density distribution. Only the biggest challenge was that deformation during firing. I think here it is on room temperature and low temperature. So that also is means not there. So advantages are more here. Product quality, consistency, all that is good here. And we can expect properties distribution within, I can say, plus minus 1%. Purity is good, shaping is good, all that. Now biggest challenge is that here, commercialization, we were working on the geopolymer, and geopolymer, lot of benefits, eco-friendly, that is one plus point. Then this circular economy, that was plus point. Here also that Dr. Madhu said circular economy. So all those benefits are there. But geopolymer, cement also, products also, all are good. So, but now that additives what we were using for geopolymers, that price has gone up. And geopolymer based products again have become costly than regular traditional cement based products. So cost is the biggest challenge, and shaping, all those are the plus points. And one this thing that machineries, if we want to produce advanced ceramic components, machineries were biggest challenge. Here it may not be there. So with all those benefits, I think cost is the biggest challenge for commercialization of this technology. Yeah, with this I am done. Thank you.
Thank you. Do you have questions?
We started about 20 years ago with the development of own pre-ceramic polymers, and the costs at this time were already very high, and also the availability was strongly limited. And therefore, we had a discussion in the past with Clariant and then with Merck, how we can make or create a bigger market for precursors. Because when we compare the polymer market and the market for metals, the ceramic market is only a niche market, in summary. And then the PDC market is a niche market in the niche market. And therefore, we had a discussion to look for applications of the precursors in the field of polymers, because this is the biggest, and this could lead to an increased production of the precursors, and therefore we could limit the price. And therefore, we started also to develop coatings, not only ceramic coatings, a lot kind of polymer coatings. And maybe this could be also helpful to lead to a stronger growth of the PDC market. In summary, Ravi, you are the founder of a startup. Can you tell us about the problems of the funding of such a company? I think it's
yeah,
not so easy.
Yeah, I thought, in fact, I would ask this question to you and Samuel. See, we have around 50 advanced material startups in India, and out of them, ceramic startups are very limited. And mostly because I think the biggest challenge in incubating a company in the area of materials is the investment. It's usually capital intensive, and also long development cycles. And it's very difficult to convince venture capitalists many times in this area. So that is one reason it's not so easy to incubate companies. And in fact, Dr. Ganesh Babu, who worked with Dr. Ranjit Devasi and VSSC, took the bold step, and along with PhD student and Dr. Abha Bharti, who also worked in Vikram Sarabhai Space Center, they took the bold step to incubate a company. But the good thing is that we have a ecosystem here. We have the research park, which is close to campus. So there is an ecosystem to do that, but it's not an easy thing. It really took, I think, something like 2 years to get convinced that you can take such a bold step. Yeah, funding can be there, but we should also see what are the business models should be clear to us, and who will be our potential customers. And as you rightly said, most of these precursors are typically used for strategic applications. So obviously our customers will be from the strategic sectors. Of course, there are private companies who can also be there, but then these are some of the challenges that we face. In fact, I wanted to ask the same question to Samuel and you. You have been working on precursor development for a very long time, and why did you not incubate a company?
Yeah, that's a very good question. And we had a pilot plant in Bayreuth to produce about 5 kilograms of precursor per week. And this is really a hard business. And I think the biggest problem is for most of the companies, the return of investment. When we look back to the developments in Japan in the 60s and in the 70s, it was not a problem to develop a ceramic fiber within 10 years, because you need such a long time to develop a ceramic fiber. It's the most complicated processing of all products, and they had the passion and the money to develop such a ceramic fiber. Nowadays, such a development is nearly impossible in Germany. You cannot start such an activity. We have the knowledge, but no company would like the risk to develop such a company in such a product. In Bayreuth, we have a kind of startup. It's called BJS. They try to develop a silicon carbide fiber, but also for this company, the business is very, very hard. And also the expected time for the development of such a fiber is already exceeded, and nobody knows what happens when they are not successful this year. That's at the moment the problem. The expectations are too high, and the return of investment is too fast, or should be too fast.
Samuel, you want to add?
Yeah, I just need to confirm what Günther said. I mean, we are working with a big company in France, for instance, Safran Ceramics, and they always ask us if we are able to produce big quantity of polymers. I mean, big quantity means several hundred kilograms of polymers. Of course, you cannot do it at lab scale. And, but we are scientists and we are not trained with the development of startup. And maybe our vision is too short and not not linked with the vision of industrial partners. And I think for me it's an issue to develop such a startup because I am not an expert and I have not the vision of industrial partners. And the time. You need time to, so you need to find a good person to be associated with this person to create this startup. You need time to develop it. And yeah, and it's another job and to fight against the bureaucracy, yes.
Yeah.
So this is why I stay at my level and but I have always this in mind to create a startup, but I need someone that can convince me. Maybe you.
Okay, thank you. Professor Mathur, I wanted to ask you a question. You are a chemist, you are a processing specialist, and you are currently also the president of the American Ceramic Society. So both as an academician as well as somebody who is leading the American Ceramic Society, what is your perspective on both in terms of research, where we are, and what are the difficulties with respect to commercialization of such products? It need not be strategic. I mean, if you have ideas where it could have also been in non-strategic industries, why such a thing has not happened, if you think that has not happened?
Right. Thank you, Ravi. I think I will come back to Acer's part later on. Since it's an Indo-German workshop, I would like to first look at both systems. And I think now being raised here and have done my doctorate here in India, I know this system well, and I have served in Germany enough to compare. And this is something we have as the major motivation to hold dialogue like this is to learn from each other. Germany is a country which is not very rich in natural resources, but very strong in engineering of products. I mean, we all know made in Germany is a quality symbol for some reason, because they have very strong model of technology transfer. So from the good ideas from university, they go through an incubator. This can be Fraunhofer Institutes, for example. The startups are there. And I think this is something which has also allowed to sustain, during the two economic crises, the stability of the economy. Now, and I think this is why I'm saying this, because this is still going on. But what is the limitation in the German system is that it's a limited market. How much can you do for 85 million people, and even looking at the whole Europe? India being a huge market, it's an automatic partner. There is a reason that Merck is producing in India. 100% facility is producing because this is where the consumption is. So now why the technology transfer is not happening on the Indian market? The reason is we don't have the SME culture. Because we have institutes like IIT, smart ideas, great, and then we have these global companies who will do their global shopping in terms of like patent, technology, application, but nobody is there to do the hand-holding for somebody like I spoke to the Sera Tattva people. Excellent work, and this community can definitely give a push to this, that the people are. But so I always say that India, we have a lot of gods, but we don't have angels. We need angel investors. And this is where I think is the biggest bottleneck, that we need to come forward to really create this culture, and industry can come and do hand-holding, giving the initial funding. That's most of the startups which are based on technical products, they die within 3 to 5 years for this reason, that you don't have enough money and resources to overcome this valley of death. So this is where we need people who are willing to invest and to come forward. So, and I think here we can definitely learn from, there is interest of Fraunhofer Institution to start something similar in India, and I think India has a huge ecosystem. We need many of these organizations because we are good at TRL 1 to 4, and then maybe 7, 8, 9, 10. So I've been advising the Society for Surface Protection, and they are all paint industries. They buy all their pigments from outside, advanced ceramics, and Dr. Sharma just mentioned. We don't have advanced ceramics manufacturing here. So this is this level. Second, if I come to the level of I being a university educator, my best products are One is sitting here, a PhD student. So who is able to work in the lab? So my mandate is, and I have done this. I was participating in a company long back when I was really convinced with the precursor processing idea. And then I realized we produced several batches, but there was no buyer. Who's going to buy them? And then all the German regulations. I just thought my ideas, my chemicals, and the cost of storage, energy cost, all those things, I didn't have that business model in my mind. So by the time you start making money, it's such a challenge. So this is the second thing that we need also, transfer scouts from the industry coming and mentoring a particular process to go to that, right? And the third thing I think, which is at now a molecular scale, is that polymer-derived ceramic is a great approach, but we have to really analyze it. Have we left the academic realms and are we really in the industry frame, or we are still talking about something which is industry relevant but not industry ripe? And this is where I see the main challenge is, if I compare the organic chemistry, polymers, there is a high predictability. You can produce it in India or Sri Lanka or Japan or wherever, US, you will get the same tacticity, same molecular weight. PDC is a science which works differently in different hands. So I think this is where we probably need to, in a community like this, use the data management and really see that we have standardization. We have parameters which can be repeated, and you have a product we say, okay, certified by Saira Tatva, it works everywhere. So this is, I think, in my opinion, these are the main challenges, but I'm sure there are other ideas. So thanks.
Thank you, Sanjay. I now want to ask Dr. Devasya, because he comes from the space industry. And you know that being from the space industry, it is not so easy to collaborate with people across possibly the country, outside the country. And you may have your own restrictions and so on. So how did you, or how are you managing?
Sir, I will just put it like this. The organization itself understood the importance of polymer-derived ceramics only in 2005. Even though we had stalwarts working on this field. And in 2005, a dedicated division was formed to work on polymer-derived ceramics, to work on high-temperature materials. The first problem what we faced was pre-ceramic polymers, to get it in bulk. So in fact, polycarbonate was the benchmark, and being in ISRO, we always had the embargo issue, it was a curse to us. The moment we get samples, but the moment we ask in bulk, we do not get it. That is one of the reasons why borosiloxanes were made in our laboratory, because that was an economical option as a matrix resin. Okay, but then borosiloxane has its advantages as well as its disadvantages. We tried procuring polycarbonate from different sources. The cheapest source was China. Due to obvious reasons, Chinese sources are all restricted now. Then we were forced to explore we had a process for polycarbonate in the laboratory level. In fact, we did an industry exploration to look at suitable partners for ISRO to handhold to bring polycarbonate to an industrial level. Now this I'm talking about a story in 2012. At that point of time, precursor-derived ceramics was something new to the industry. There were very less takers in the Indian market. So we put exploration in the market, we got very little responses. Out of the responses, the organization sent a committee to look at the industry, their capability, because we wanted it in bulk. Now another question the industry asks, see, for example, I set up a facility for polycarbonate. What is the buyback guarantee you have? See, many of the missions, leave aside the commercial missions. We have PSLV, GSLV, LVM3, which goes like you have 10 missions per year. But the high temperature, the re-entry missions are all experimental missions at this point of time. So what is the quantity I can commit to the industry? Because they are going to set up something. Fortunately, we found out some vendors, we could handhold them. The batch what we gave for polycarbonate was a 300-gram batch. We could support them. Even in spite of the failures, we bought the polymers back because we didn't want the company to run into a loss. Now we have matured into a 4-kilogram batch. And that industry has been enabled to give us 16 kilograms per month. That is, they can make one batch, but they can easily scale it up. this is with a buyback guarantee. Now, at least in a year, for the next 4 years, I'll be buying 400 kilograms of polycarbostyrene from that industry. Even then, it works out to be cheaper than an international source. So the major question which might come to Saratatva also, because when we are looking at industries to be our partners, this question will come back to us from Saratatva. How long are you going to support us? So this question we have to answer. Till now, we have been supporting the industrial partners to a good level. We have a minimum buyback guarantee so that the industries also need to sustain. And we also encourage the industries by means of technology transfer, because ultimately we use the public money for our development. So the technologies what we give back to the industries are very cheap, at cheap rates, so that the industry is not at a loss. So this is what I think, because we are having products coming in line, which we will be coming back to the industries so that they will be hand-holding. Then one more thing is that as per the government rules, we cannot go on buying the same product from the same industry beyond 5 years. Beyond 5 years, we are supposed to find another industry, another vendor. You need to have a fallback option. It should not go to one industry. So nowadays, the government policy, the department policy is also to find out multiple vendors so that you get sources, multiple sources for the same product. So I think the government is also giving a proactive role in supporting the industry. The space sector has opened up. So I think that's it from my side.
I just want to add one comment. See, we cannot sell any component as a polymer derived ceramics because customer doesn't appreciate what way it is made, right? Because they want some specific performance. So our attribute has to be something different. So when it goes to a system, finally the system performance is important, like what Dr. Ranjit said. Finally the performance at the space, that is important. So we need to select the right component or the system where PDC can be used. Because I was thinking last few days and today also, what are the things which I am doing, can I replace by PDC? But when it comes to the cost, the manufacturability, then again I have to think back. And availability of material, I was discussing with your team also. So we need a more material. If I want to make some component, I'm trying to do it. It's very difficult to make now by conventional method. I was thinking, can I make by PDC? So, but finally my customer doesn't want any PDC or anything like that. He want a product with that performance. So maybe we need to identify the specific application, especially strategic applications, or some other thing like coatings, or combination of like modeling that CVD and PDC coatings, combinations, like that coating on SIC composites, just a coating. So these are the few areas we need to identify that has to be commercialized. That is what I feel they should commercialize with specific application in mind. And try to attribute for the final properties, final performance.
Thank you. Samuel, do you have been working in the area of PDCs for quite some time, maybe 20 years already. Yeah. So where do you see 10 years down the lane what we would be doing? And also we have a lot of young researchers here, and this was one of the other ideas to have young researchers here. And
I think one of the future of PDCs is maybe going to energy, especially to catalyst. Electrocatalysis or photocatalysis or electrophotocatalysis. Because especially low temperature process, we saw a lot of example of metal containing PDC, and this is very, I think, a very nice process because you can form in one step the support and the catalyst. And if you can, if these catalysts are accessible, I mean, if these metals are accessible, you can use these materials for catalysis, and I think this is one of the future of these PDCs, in my mind. Okay. And also 3D printing, if you can design such materials as electrodes, this can be very interesting here. This is one way. Yeah.
We are all teachers from universities, and I think what we can do is to educate the students, because later then they go to industry, and in Germany we have the problem that the engineers, or when someone is constructing a machine, they always prefer metals because of the brittleness of ceramics. And therefore, they try always to avoid the use of ceramics. And now our task is, I think, to educate the students, to motivate also to use ceramics, to look for the advantages of the ceramics, that we can introduce our products much easier to the industry.
Should we take some questions from the audience?
Yeah.
You want mic? This mic.
First of all, thank you. I'm happy to see you all on the stage. And my question is, since both Germans and Indians are here, I want to know how does each of your governments are supporting this kind of technologies when you compare. So what are the differences, which is any better plans are there so that we can get those plans to the India or to the German, vice versa?
Was the question related to technology transfer in the area of PDCs between India and Germany?
So basically the government,
or in general?
Yeah, I got your point. You're saying what are the government instruments to really help make this thing happen? And I think in terms of global challenges, that's the one good side of globalization, that the governments are aligning to one unified agenda. So hydrogen, for example, is not a technology which is only focused in Germany, it's everywhere. You look at the Green Deal in Japan is the same. You look at the hydrogen roadmap in India, it's the same. But everything, all these challenges, these are important for sustaining our future and future of the societal well-being. And they all relate somehow to materials, and advanced ceramics are playing a very big role. This is one thing that every government has. The formats may be different, but the need that we are too late in addressing the challenges of our planet is identified everywhere. You can see the G20 summit that will be in September in India, the pre-meetings. So the agenda is very much homogenized worldwide, and that's one good thing. I think the important thing is, how do we, as we are looking at, how do we make materials attractive for certain application at the cost? Because this is like a three-body problem: academic innovation, technology transfer, and commercial interest. Any venture capitalist or any industry holding hand is looking for return on investment. So this is where we need to work on. And I think the common link, in my opinion, is the current understanding of even non-scientific, non-academic people about sustainability. So if you look at sustainability, is not only circular economy that you can recycle something, it's also, for me, the longevity. What is the lifetime? And if you look around, what has survived the evolution of our Earth or planet, these are ceramics, all rocks. So I'm optimistic that ceramics, once you make them in the right form, they are going to address some of the mega challenges of energy. And this is, I think, or clean water. I think we are right now focused. And in India, I know that when I travel now, I see when we never had issues with flowing water. Now we have water cuts that we have only. So I think water will become a big, and that means we need resources for water remediation. And again, we need to decrease the waste. And this is where I see the polymer-derived ceramic, and I think Ravi just mentioned that if you can chemically link something at the molecular scale, you can reduce the temperature of processing, the density can be controlled. So there are options here that relate, this small observation relate to the mega challenge.
Thank you, sir.
Yeah. Is there any question? Yeah, Oliver.
Well, it's more a comment than a question. I've noticed, so I'm not a polymer-derived ceramist, basically, but I am quite well integrated in the energy sector. and know that it's very challenging. Here, everybody is talking about PDC as possible anode material and so on, but one has to take into account that we are not the only one to work on this topic. There are plenty of other alloys, of other compounds which could be suitable as next generation or next generation of anode materials, and it's very useful and necessary to benchmark what is done in the community or elsewhere with the best current materials as substitute for graphite, I mean for lithium, but and so on. It's just an example, but because the battery makers, they don't care if it's PDC you mentioned before. They don't care. They just want a product which is cheap, which works better than the other. So that's why it's also difficult, yeah, going from the simple ceramic expertise and knowledge and to reach out and try to understand and to enter this world of batteries or whatever, or catalysis, because catalysis is also very complicated if you want really to think up to the system, to the reactor and so on. But I think it's necessary to team up with other groups, with other expertise, and different companies and research institute, because otherwise you are working on a small isolated problem, and the likelihood that it brings something up to a commercial product is very, very, very small. So it's a general observation. I don't say we are doing particularly better, but we try to have this in mind, this global window.
Yeah, thank you very much, Professor Guillaume, for the honest observation. Yeah, maybe last comment from Professor Loosdrecht. Yeah, there. Oh.
Hello, sir. This is Dr. Abhishek from CMET Trishur. So I come from Electronics Center for Materials for Electronics Technology, and Mathur sir may be aware of that. Sir, I was working on PDC on my doctoral. After that, I joined CMET, and then I started working on piezo materials and other dielectric materials. So I was thinking whether after the post-COVID era, we have seen that semiconductor shortfall, and there is a government is also putting a lot of efforts in establishing semiconductor setup in India. So whether PDC work can be aligned to this dielectrics or semiconductor industry? That's my question, sir.
Can we also take one more question from Professor Loosdrecht so that we can answer both and then close?
I mean, one of the things which, from my point of view, which is most important is somehow the success of this transfer. It's a bit what Olivier also said, and what was said, that eventually you want to have a commercial project, so you have to compete with whatever other materials there are in the world. And this is where, in my opinion at least, scientists and teachers are particularly weak. They have an enormous amount of ideas of what one could do, but have no clue, typically. I exaggerate a bit, how this really works out in practice, how to upscale, what is the real commercial value. And there I have more a request than anything else, or a suggestion of, at least from general universities, we still go a little bit from inside the university, try to go outside. We have people like transfer scouts. They come more or less out of the university environment, and they have no clue about, let's say, these more economic questions and the materials. And what should happen much more, in my opinion, is that from the companies, transfer scouts indeed help essentially the scientists to do the technology transfer and to do it where it's useful and not where it's not so useful. Because there's a lot of brilliant things going on, but that's the scientific part, and the application part is really something else. And as I said, I don't think that the people in the universities, including myself, have enough knowledge to be capable of doing this, and we need help.
Yeah,
it's a remark at the end.
Thank you, Professor Paul, for the comments. But to answer Abhishek's question, would you like to answer, Samuel? PDCs in the semiconductor industry? Nobody has any idea at this point of time. maybe we discuss this in the beach. Yeah.
Of course, you can have some semi-conductivity in some composition of PDCs, but I have no idea about the application of these materials in terms of cost, in terms of processing. It's difficult to answer. Yeah. Maybe Ravi?
Yeah. In my group, we have been working on producing some of the dielectric materials using PDCs. I would say during the last 2-3 years. But we have, to make an honest assessment, we have very mixed results. But we are exploring possibilities of using PDCs even for the next generation communication devices. But I think it's too early for me to comment on that. I think if we have more results to share in the next 2-3 years, and if it's very positive, then we'll be able to share. But I believe it's possible. We are in the very nascent stage of this work. So I think, maybe this will be the last question.
My question is, how we can integrate this PDC technology with the existing technologies where people produce products that goes into the market. So how far it is to the market?
It's already in the market. A lot of products are already in the market. Yeah. Ceramic fibers, ceramic brakes, for space applications, there are many products in microelectronics. It's already in the market, but the market is very small. That's the problem in many cases.
Maybe I just, as I mentioned earlier, maybe you have to create some USP for your material, so that can add value to the whatever existing product. Like whether semiconductor material, already well-established materials are there. India is going to manufacture the same thing. I'm not going to invent something new, right? So in that, is there any material which can be used for LTCC, MLCCs? Somewhere it can be used. So like alumina, you are manufacturing. Can you make some alumina which can be sintered at low temperatures so that can be used for LTCC like that? Maybe some USP, maybe you have to find out which can be integrated to the existing product. That's what I feel.
Yeah, I would like to add something like to the industry. See, we are looking at value-added products. Currently, the benchmark with respect to the TPS might be rigid TPS. Maybe it's carbon-carbon or CSIC. But logically speaking, we would like to have TPS which are more rugged. So the logical option would be to go to USTCs. But it's not very easy to simply swap the matrix from silicon carbide to USTC. You have to you have to improve from the fiber level itself. Currently, most of us, when we work at CMCs, we end up with the T300 class of fibers. So why not we have a better class of fiber? Yesterday, Dr. Mose was talking about a fiber inherently oxidation resistant, apart from silicon carbide. And silicon carbide fibers are very expensive. Well, carbon fibers are cheaper compared to silicon carbide fibers. But if we have a carbon fiber in the core with a silicon carbide coating or something like that, which is cost effective, that is one aspect. Now, when we talk about the interfaces, we have only two candidates. One is pyrocarbon, another is boron nitride. Now, boron nitride, the limit is around 1400, 1500 degrees centigrade. What if we have interfaces which work beyond that? Like a combination of boron nitride or pyrocarbon or something, BCN interfaces. Now, again, one more thing is the UHTCs, when we talk, or the CMCs, when we talk, CVI process is one thing. Dr. Uday is here, who is an expert in CVI. Now, CVI, all said and done, it's very slow. Now, people are working on film boiling CVI. Now, when we have film boiling CVI, the precursors for carbon is well known. But what about ceramics? That is where the industries or the young generation can come with the ample precursors for film boiling. With film boiling CVI, we end up with a CMC in 1 week. Rather than 6 months, what we do with the CVI process right now. With 300 hours of infiltration over 6 months of time, you get a CMC in, let's say, 7 days' time. So that is one aspect. Then I think, see, currently we are all restricted with rigid TPS. Why not flexible TPS? It's a food for thought. Imagine a TPS which is kept inside a canister, I'm talking about re-entry missions, and during re-entry, like an umbrella, it is open. It need not be composites. It can be fibers, flexible fibers, impregnated with appropriate pre-ceramic polymers. During re-entry, it can take the heat of re-entry, convert itself into a ceramic. It can be a throwaway system. Halfway through, you can just eject it, but the mission is safe. It's just a food for thought for the youngsters to do. I don't know. It may come. It may be flexible. I don't know.
Yeah. Thank you, Dr. Ranjit. I think we have now been talking for close to 1 hour. We thought we'll close in 30 minutes, but I think it's time for us to close because we also need to start in a few minutes. So we close the discussion right now. I think there are a lot of things to discuss and there are a lot of challenges. I think material development, as I said, it usually has very long development cycles. It takes time. I think one has to be patient to see applications at some point of time. So I think with this we close the discussion. I thank every one of you for coming here and offering your inputs. We are very grateful to that. So maybe as a token of appreciation from our side, we have a few gifts again.
Thank you very much, sirs. That was a great discussion. And we feel privileged to hear what all you have in your minds. So I request Dr. Ravi Kumar to present memento to Dr. Ranjit Devasaya.
I think in order to have time, we will first start giving. Oh, you can take it.
Dr. Sanjay Mathur, sir.
Like Christmas. Thank you.
Dr. Madhusudana.
Yeah.
Dr. Yogan Martis. Dr. Lalit Kumar Sharma.
Thank you. Huh? That's okay.
Dr. Ranjit Devasaya.
You are getting a small one. This is supposed to.
I'm youngest of the lot.
Thank you. Yeah, thank you so much. I think we will meet here at 4:30. So the buses are already ready. You are free to go to your guest house and change if you want, and then please be here by 4:30 sharp, because it takes 1 hour for us, 1 hour 15 minutes. Oh, there's coffee. Please take coffee and then. I forgot about the coffee. Please have your coffee and then you can go. Yeah.
Thank you, Ravi. Thank you, everyone.
Thanks for reminding me.
Hello. One small announcement. Whoever wants the cab to be arranged for their